여러분 안녕하세요. 오늘은 제가 여기 보이시죠? 구글, 여기 역삼동에 있는 구글 코리아 사무실인데요. 오늘 여기서 기자간담회가 있어요. 근데 여기서 구글 관계자들이 다 오셔서 하는 건 아니고, 지금 일본 도쿄에서 제프 딘 맞죠? 그 사람이랑 아시아 태평양 기자간담회를 하는데, 지금 도쿄에서 열리고 있는 걸 실시간으로 여기서 스트리밍으로 보여준대요. 그래서 당연히 동시 통역 해주고요. 저 같은 영어를 못하는 사람한테는 커피가 지금 사무실이 참 예쁘죠. 이제 저 기자 간담회가 시작되는 곳은, 잠시만요, 저쪽 안 보인다. 저 문을 들어가면 되고요. 이렇게 생겼어요. 10시부터 2시간 동안 한다는데, 당연히 이게 14시 2시 엠바고여서 실시간으로 제가 보여드리지 못하고, 2시간 동안 튼다고 해서 다 보실 것도 아니니까 좀 중요한 부분들 좀 잘 편집해가지고 보여드릴게요. 오늘의 주제는 인공지능의 미래? 머신러닝? 뭐였더라? 잠시만요. 자, 구글의 최고 연구원, 그리고 이 프로덕트 리더가 아닐까요? 구글 제품에서부터 헬스케어, 환경, 이 사회적 문제에 이르는 다양한 분야에서 인공지능이 어떻게 활용되고 있는지 보여준다고 합니다. 그리고 이게 어떻게 미래에 이점을, 사용자들에게 어떤 이점을 제공할지 발표를 한다고 하는데요. 사실 구글이 요즘 그 개인정보 무단 사용에 대한 이슈가 있잖아요. 그걸 의식해서인지 아니면 그냥 실시간 스트리밍이어서 그런지 모르겠지만 질의응답은 받지 않는데요. 그래도 혹시 또 뭐 기회가 있을지 모르니까 이런 이슈, 또 구글의 세금 문제에 대해서 어떤 좀 생각이 있는지 한번 물어보도록 하겠습니다. 그러면 제가 이따가 그 인공지능, 머신러닝 뭐 이런 다소 어려울 수 있지만 미래의 기술, 우리의 4차 산업혁명, 그놈의 4차 산업혁명, 그거를 이끌어가는, 우리가 알아야 되잖아요. 제가 한번 잘 담아보겠습니다. 그럼 기다려주세요.
여기 영상에서 나오는 소리는 저도 확실히
방금
여기서 하시는 거 완전은
그럴 것 같죠? 네, 여러분 이제 안에 들어왔어요. 이렇게 동시통역 보이나? 동시통역 이거 줘가지고 이거 이제 들으면서 할 거예요. 지금 9시 58분인데 이제 2분 뒤면 시작하거든요. 그래서 저기도 이제 준비하고 있고, 제가 이제 화면을 저기 화상으로 돌릴게요.
주최하는 행사를 화상으로 연결을 해서 생중계를 해드릴 예정이고, 한국어 동시통역이 제공되니 통역이 필요하신 분께서는 리시버를 착용해 주시면 감사하겠습니다. 이번 간담회 주제는 Made with AI인데요. 구글이 그동안 모두를 위한 AI를 실현하고자 어떻게 노력을 해왔는지, 또 어떤 성과를 거뒀는지, 그리고 앞으로 어떤 과제가 있는지에 대해서 약 2시간 동안 발표를 가진 후에 질의응답 시간으로 이어질 예정입니다. 그리고 사전에 공지 드린 것처럼 오늘 기사 엠바고는 오후 2시인 점 양해 부탁드리며, 영상과 취재하신 내용 모두 오후 2시 이후에 릴리즈 해주시면 감사하겠습니다. 그리고 오늘 질의응답은 현장 질문과 각 나라별 질문을 섞어서 할 예정인데요. 질문이 있으신 분께서는 저희 자료에 보시면 질문을 적으실 수 있는 종이를 같이 전달을 해드렸습니다. 그래서 발표가 끝난 후에 질문을 적으셔서 저희 스텝에게 전달을 해주시면 저희가 현장에 전달을 해서 질의응답 시간에 반영이 될 수 있도록 할 예정입니다. 그리고 저희가 모든 나라에서 같이 질의응답을 진행할 예정이고, 질의응답 시간이 한정되어 있어서 반영이 되지 않을 수도 있음을 미리 양해해 주시면 감사하겠습니다. 저희 오늘 키노트 중에 파트 1은 곧 10시에 시작을 할 예정이고, 영상과 동시통역 같이 들어주시면 감사하겠습니다.
So hi, good morning everyone. Thank you for coming. My name's Tim Chapman.
I'm Jeff Dean. I lead the Google Brain team, which is Google's artificial intelligence and research team, machine learning research team in Mountain View, California. This is my first time in Tokyo, so I'm pretty excited to be in Japan. My wife and I just arrived yesterday, and I don't speak Japanese, unfortunately. So one of the things that machine learning can do is to make sort of the rest of the world much more accessible. And so I'm going to just give you a symbol of how that's working. So one of the things we can do with our new Google Translate app is I can see a sign like this, and 10 years ago, it would be impossible for me to read what that says because I don't speak Japanese. But today, if I, let's see, we could cast the phone. So I'm going to head over here. I'm going to show you that, and now, oh, it's not showing the phone. Second. Are we casting the phone? Okay, there we go. This worked 10 minutes ago, so.
You're not able to ask them. You'll see Highlands and West.
Oh, there we go. Yes, it was to cast. Okay, here we go.
There we go.
So, there's my phone, and I just open up the Google Translate app, and I can just put the viewfinder there, and it now shows me what that says in English. And I can pick, other languages if I spoke other languages. So I think that's an example of something where, that's made traveling around in Japan or in other countries where I don't speak the language much easier by being able to do that. So can we get the, so ultimately what our goals are threefold. So one is we want to use artificial intelligence and machine learning to make our products more useful. And that's a good example of that. Second, we want to help businesses and other external developers innovate using machine learning and artificial intelligence in solving their own problems. And three, we want to provide researchers with the right tools, both our internal researchers and external researchers with the right tools to tackle really large challenges in building artificial intelligence systems in the future. But first, I want to answer three important questions. So one, what is artificial intelligence? Second, why is this happening? Why do we care so much about it now? And why do we care so much about it? So, artificial intelligence is this concept that has captivated computer scientists for more than 50 years. Very soon after computers were invented, people wanted to have this notion of being able to make machines that were intelligent in human ways, that could understand and could reason and could perform similar kinds of tasks to humans. And for a long time, the science of artificial intelligence was actually much more rule-based. We were trying to define logical procedures via hand-coded rules in order to make machines intelligent. But in the last 10 or 20 years, I think we've realized that it's very, very hard to encode everything about the world as logical rules. It's almost impossible to come up with rules that allow me to say, is this a cheetah or a jaguar or a giraffe, right? It's very hard for us to do that. And so the science of machine learning has really taken over the field of artificial intelligence because we believe that machine learning, which is essentially allowing machines to learn from observations about the world in the same way that humans and other animals do by learning to recognize patterns and things like that, is actually a better way than writing hand-coded rules. So at its core, machine learning is this new way of creating intelligent systems, essentially collecting data sets, exposing machine learning algorithms to those data sets, and then allowing them to generalize and to make predictions and classifications instead of writing hand-coded rules. A good example of this is the difference between the approach taken by IBM in their Deep Blue chess playing program about 15 or 20 years ago versus the approach taken in AlphaGo. So in Deep Blue, chess turns out to be a complicated game. It has about 10 to the 50th or 60th different board configurations. But it's a game where you can actually have hand-coded rules and patterns. And in Deep Blue, they used some chess-specific accelerated hardware. And with that, they were able to make a system that could actually play chess and actually beat the world champion, Garry Kasparov. So Go is a much more complicated game. It has about 10 to the 170th possible configurations. And so you really need, you can't have enough computing power to really exhaustively explore the space of board positions in Go. And so you really need a system that can learn how to recognize interesting patterns that occur during gameplay and to learn kind of the intuitions that a human Go player has about, this seems like a good place to move, I should definitely not move over here. And by using machine learning, we're able to actually expose the system to games played by humans and learn how to play Go from observations of those kinds of patterns. And so that was essentially the work behind the AlphaGo team that played Lee Sedol in Korea and then Keji in China. So machine learning is really teaching computers to learn without having to program rules. We write very simple algorithms about how to process data, and then the system learns from that data. One of the most popular kinds of machine learning these days is something called neural networks. So neural networks are these systems that are loosely inspired by how biological brains behave, and that they're structured in layers, where these layers tend to have individual neurons which recognize certain kinds of patterns, and then those neurons are connected to other neurons, often in later stages of processing. So here we have a neural net that is going to process images. And the first layer is connected directly to kind of the pixel values in an image. So it looks for different kinds of patterns, in the first layer where it might find, edges at different orientations, or does this small patch of the image contain a mostly brown, or is it mostly green? And then as you go up, the neurons now become functions of other neurons, the outputs of those other neurons, and so they learn more and more complicated patterns. So they learn, does this part of the image contain a corner? Or is it an edge with green on one side? Or, as you get farther up, is it like an ear or eyes or whiskers? And the way we're going to train these models is the key to machine learning. So we're going to take one of these images, let's say that cat, and we're going to feed it through the network. And at the end of the network, we're going to make a prediction of what kind of image that is. Is it a cat or a truck or an apple, or maybe dozens of other categories, maybe even thousands of categories. And we're going to see what the model predicts given that image. If it makes the correct prediction, we're done. But if it makes an incorrect prediction, we're now going to take the model and make little adjustments to all the neurons and the behavior of the model throughout the whole set of layers, so that the next time we see that image, we're going to make, we'll be more likely to make the correct prediction. We'll be more likely to say cat when we see that image than the last time. And ideally more likely to see, say, cat on similar images. And by exposing the model to thousands or millions of training examples where humans have labeled what the correct answer is, we can essentially learn very complicated functions. So we're going from the raw pixels of an image to the correct label of cat. And the whole reason we want to do this is so that when we see a new image, an image we've never seen before during the training process of the machine learning model, we can actually make a prediction for that image as well. So here we have a new image, and we're now going to run the pixels through that model, activate all the neurons there, and the neurons in the other layers, and eventually make a prediction. And in this case, we're going to say dog, because we got it correct. And so now we can have the ability for this model, this artificial intelligence system, to label, given a classification, to an arbitrary photo. We can take any picture and run it through the model, and it will give a prediction. And if we've done our job right and trained the model well, then it should give accurate predictions. And it's not just giving an image and giving a category for what is in that image. We can train neural networks with lots of different kinds of inputs and lots of different kinds of outputs. So think of it as being able to learn very complicated functions from input to output. So we can take in the pixels of an image and predict a category out of, not just 5 categories, but maybe 10,000 different categories. So that's a lion. We can take in audio and a sequence of audio features, like a recording, and say, transform that into a transcript of what is being said by doing speech recognition. How cold is it outside? We can take English text, hello, how are you? And transform that into the corresponding text in another language, ni hao ma. We can take the pixels of an image and not just produce a category, but produce something like an entire sentence that describes that image. A blue and yellow train traveling down the track. Right? And that actually requires a fair amount of understanding of what is going on in the image. It's not just a single category. We have to know that that's a train. We have to know that it's blue and yellow. We have to know that there are tracks. So these are quite complicated functions that these systems can learn. And that's, I think, why people are very excited about this, because if you collect the right kind of training data, you can build very powerful features and systems that can do really interesting things. Which is essentially why Sundar Pichai, our CEO, has really said that now is the time for Google as we shift to being an AI-first company. We've always been working on problems that we know artificial intelligence will help solve, things like search or translation or photo understanding. All of these things require deep levels of understanding of the data that they're seeing. The better we're able to make those systems, the better we'll be able to make our products. Today we have 7 products that have over 1 billion users. And so by improving all of those products using machine learning and artificial intelligence, we'll be able to have a really big impact on more than 1 billion people. That's really significant. So our group actually started doing research on the use of deep neural networks, in particular very large deep neural networks, in 2012. And one of the things we did at that time was we felt like if we could scale up these models so that they had much more computation and many more neurons and many more connections between those neurons, we would actually be able to make very powerful models. And so at the time, a typical neural net might have between 1 and 10 million connections. And in 2012, we did some research where we used many, many computers in our data center to train a neural network with more than 1 billion connections. So 100 times larger at that time than sort of the biggest neural nets that existed. And one of the things we did with this neural net is we did an unsupervised training task. So what I showed you before was a supervised task where we had images and we had labels about what is in each of those images, and we tried to get the model to learn those connections. In this case, what we did was an unsupervised task. We just exposed the system to a bunch of images. In fact, it was just single frames of a bunch of random YouTube videos. And we tried to have the model learn patterns that occur a lot in those millions of images. And since it's YouTube, one of the things that the model learned was one of the neurons learned to be sort of responsive when the image contained a cat. We all know YouTube has lots of cat videos. So this is kind of this ideal stimulus for one of those neurons. And starting from nothing, the system essentially invented this concept of a cat by purely being exposed to lots and lots of images, some of which contain cats. And we used this model to improve the accuracy on an image classification task at that time. The other thing that we're really working towards is sharing the tools that we're building for our own research with the world. In 2014 or 15, we started working on our 2nd generation of software for doing our own research and for deploying these kinds of deep learning models throughout our products. And the system that we built was called TensorFlow, and we decided we would open source that so that the rest of the community could benefit from the work that we're doing and use it as a way of exchanging machine learning research ideas and use it as a way of trying machine learning and artificial intelligence in lots of problems outside of it. TensorFlow is now the #1 repository for machine learning on GitHub. It's had a lot of success as people have really adopted it and tried it with lots of different kinds of their own problems. You'll hear about some of those today. This is a chart that shows kind of the popularity of different open source machine learning toolkits that are hosted on GitHub. And you can see TensorFlow has had a pretty steady ramp of adoption and success. And you'll hear more about TensorFlow from Kaz Seyfel later today. So why is this happening now? So neural networks and the algorithms we use to train them are not actually that new an idea. They've actually been around for 30 years or more. And in the 80s and 90s, people were very excited about neural networks because they seemed like they were kind of the right way of approaching some of these problems. But the real challenge then was that we just lacked enough computational power to really make them work well on real large-scale problems and realistic data sets. They would do interesting things on toy problems, but when you tried to scale them up, we just didn't have enough computing power. So now, thanks to Moore's law, we have computers that are 1,000 or 10,000 times more powerful as the ones we were using in 1990. And that has really made it so that neural networks are now a practical solution for lots of problems. And as we continue to scale up and get more computation, we think neural networks are going to continue to perform even better than they are today. We'll be able to train on larger data sets, use more powerful models, train on more data, and get even better results than we're getting today. So this shift of now having enough computation power is really bringing in a new age of computing where we can actually use machine learning in a really fundamental way in the middle of lots and lots of our products. Computers can now see. So in the last 5 years, computer vision has gone from not really working very well to working extremely well. That's an extremely transformative event. If you think back when animals evolved eyes, we're now at that point in computing where now computers can see, and they didn't used to be able to see. And that makes a lot of stuff possible, as you'll hear today. They can also understand what people are saying, so speech recognition is now working much better, translation is working, language understanding is working, and that is a major change in computing. So now, using this, we're now an AI-first company, and we're working to infuse artificial intelligence through lots and lots of our products. So we're going to talk about these three ways of making AI accessible. We want to make our own products more useful, we want to help others innovate, and we want to solve for humanity's big challenges using machine learning. And I'm going to go through a bunch of ways in which we've improved Google's products using machine learning. So one of them is Google Photos. So now that computer vision works, there's this sense that you can build a product around the fact that computer vision works and make all of your photos searchable without you having to do anything. You just upload photos, and all of a sudden they become searchable. So if we could get the Photos app. So let's see. I'm going to cast again. There we go. And oh, it's connecting. Okay, sorry. I think it's connecting. My apologies. It worked better without so many Wi-Fi devices in the room. I'm going to disconnect and reconnect. See what happens. says connecting. I'll just connect one more time and try it. Otherwise, I will tell you all the cool things you would have seen. All right, how about if we skip that?
Yeah.
And I will come back to it if we get it working. All right, anyway, Google Photos allows you to search your photos with keywords. So we will skip that and go on to Translate. I already showed you a demonstration of Translate where you can now use the viewfinder of your camera to translate text. You can speak to it and translate text that way. Lin Ha will be giving a good demonstration of this in a few minutes. Maps is something that machine learning can really, and artificial intelligence can really help with as well. So in many parts of the world, we're able to license sort of detailed street information for many parts of the world, like in the United States or in Japan. But in many parts of the world, there aren't providers that we can license this sort of data from. And we've always augmented all of that data we license, even in countries where we can license it, with additional imagery data, like from satellite imagery and from street view data, to use that for improving the quality of our maps and getting more detailed information. So we're now able to actually take cities and countries where we don't have any licensed data, we just have satellite imagery and we just have street view data, and actually turn that through computer vision and machine learning into actual viable, usable maps for people in those cities, even though we have no sort of concrete hand design data. And places like Lagos, Nigeria, we've done this, and the dramatic improvement in maps quality is just amazing. People really, really like that because they now have accessible maps thanks to the AI techniques we're using. You can also do things that are kind of fun. So Allo is this new communication app we have. And one of the things Allo can do is you can take a selfie, as this person, Babik, is doing there. And it will analyze your facial structure and find interesting features and turn you into this nice set of icons here. I actually did it yesterday, so there's the things it came up with for me. I look quite touching in my Allo stickers. And then you can print them out as stickers if you want. So Lens is another thing where computer vision plays a key role. So Lens is essentially making the real world searchable through imagery, similar to what we're doing with Street View and Maps. And what you see is searchable. So I'm going to just roll a video, but essentially you'll get the idea from the video.
What is Google Lens, you ask? It's a cool new tool that lets you search what you see. Here, let me show you. Okay, all you do is snap a pic, go to your photos, and tap the Google Lens icon right here. Bam! All of this information! That's so cool, right? Okay, so let's see what else you can do with Google Lens. Oh, my friend was talking about this. Let me check it out. What? Information! Fingertips! And if you take a photo of something like this, you can discover artists. Oh, I think I heard about her. You can get directions in a snap. No, literally, a snap. Ah, yes. Who was down for some art to open the mind? It even works on the triumphs of human imagination, otherwise known as art. It's all super simple. Just pull up Google Lens, get info in a snap, and live your life shamelessly.
There you go. So you can see that by being able to analyze the world around us and understand both sort of the raw things that are there, but also associate it with things like knowing that that is Coit Tower, or knowing this is an address, or knowing that this is a particular painting by a particular painter, it's really going to be a powerful thing that we can use in our day-to-day lives. The other thing machine learning and artificial intelligence can do is really make much better kinds of recommendations based on the kinds of things that you like to listen to or like to watch. So we've been using this to improve the recommended songs and playlists in Google Play Music, and also understand how people are finding parking, for example, in maps. We can actually make predictions about the state of the world in your destination and say, we think you're gonna have a hard time parking here, but this place in the past has had, at this time of day, has had really good availability of parking, and we can navigate you to that particular parking space. This is a pilot program we're running in 25 cities in the United States right now. It gives you an idea about the kind of power that you can have if you can define a predictive problem using raw data that you have available and the tasks that you want. You can actually make pretty interesting features all throughout all of our products with these sorts of approaches. Another thing that has really improved a lot in the last 5 years or so, or 4 years or so, is the understanding of pieces of text. So now we can actually really understand what text means at a level that allows us to do things like when you receive an email, we can now actually read the contents of that email using an AI system and then make predictions of what kinds of responses you might like to give to that email. So here, this person has received an email, it's a little small, so maybe you can't see it, but want to meet up for dinner tomorrow? Does 6 p.m. work for you? Right? And so we can actually make predictions of what kinds of responses make sense. And that actually requires that we understand the text of that email so that we know what responses are appropriate. But here, the system suggests, works for me, sure, sounds good, sorry, I can't. And that allows people on their mobile phones to be much more efficient with handling email, because we all know it's a big pain to sort of actually craft responses with keyboards on mobile phones. And something like 12% of all responses now sent from mobile email, our mobile email products, are sent via these little suggested responses. Another area where AI is really critical to the product is the Google Assistant. And you'll hear more about that in a little bit, but essentially, at its heart, the Google Assistant wants to understand text. So you can ask something using speech recognition, using your voice. You can say something like, okay, Google, what's the weather in New Delhi? And we actually first have to do speech recognition on that, and then actually understand that you're asking about the weather, that New Delhi is a city, that we want to pull up the weather for New Delhi, and then actually show that to you in some reasonable form. This is a quite complicated system with lots of pieces of machine learning underneath it. And you'll hear more about it later today, but that's really a product that couldn't exist without machine learning and AI that we're working on. Another area where speech recognition can really make a difference to people in the world is there are about 300 million people in the world who are either deaf or hard of hearing. And that makes a lot of video content to them pretty inaccessible. But by doing automatic captioning of the YouTube video content, of the audio, we can actually provide automatic captions. And when we have been improving our speech recognition systems, we actually can make the captions much higher quality. So we saw about a 50% increase in accuracy in these captions when we rolled out a new neural net-based speech recognition system. And we can now caption more than 1 billion videos in 10 different languages. And so that really makes all that content accessible to the 300 million people in the world who are hard of hearing. And it also makes it accessible to people who maybe don't speak the native language of the video, but can turn on the captions in their own native tongue. Speaking of translation, we did a lot of work in the last in 2016 on improving the machine translation system at Google. We've been working on this problem for about a decade, but the previous system did not use deep neural nets. It used a whole combination of sort of simpler statistical models with about 500,000 lines of code to put it all together. And the new system that we rolled out last year relied on using just simple but very powerful, trained on lots of data, deep neural networks. And so the new system is expressible in about 500 lines of TensorFlow code instead of 500,000 lines of code. And it has huge improvements in language quality. So the improvements we got in language quality when we switched to the neural machine translation system last fall were about the equivalent in accuracy to the sum of all the improvements we've made in the previous decade. And interestingly, one of the languages where the accuracy improved the most was Japanese English, English Japanese. And a lot of people in Japan really noticed that the quality improved quite substantially. We've now rolled that out for 97 language pairs around the world, and users are much happier. The translations feel much more fluent and natural and are higher quality. And we know that we can make these even better with more computation and more data. Another thing where we're combining new kinds of hardware plus software and AI are Pixel Buds. So this is a small earphone that goes in your ears, and you can walk around, and it will translate sound, language that's being spoken into your native language using the speech recognition and translation technology. And you can actually walk around and operate an environment where you don't speak the language, and with a few seconds of delay, actually get a translation in your ear of what's being said. And we think that will improve over time as we are able to run more of the computation on device and so on. So to recap, these three sort of main focus areas for us for AI. We want to use AI to improve our own products, as I've shown you a bunch of examples. We want to help others really innovate and use machine learning and AI to solve their particular problems. And you'll hear from other speakers today about other problems that they're tackling. And then we want to solve for sort of large challenges in the world, things like healthcare and ecology and other kinds of things where we think machine learning and AI can actually make a big difference. And so now I'd like to invite Isaac Reynolds up to come talk about how we're using AI to improve the Pixel camera. So, thank you.
All right. Is the microphone working? All right. Perfect. So thank you, Jeff, for that intro. I'm always amazed to hear just how many of the products at Google, from Maps to YouTube, are really powered and enabled by machine learning and AI. So I'm Isaac. I'm the PM for the Pixel camera. That's Google's smartphone. And I'm here to talk about how AI and machine learning enable all kinds of new experiences on Google devices and hardware. Like Jeff, this is also my first opportunity to come to Tokyo and really explore. So I've been taking in the sites all weekend and taking tons of pictures. This is actually a really great time to explore Tokyo because of the fall colors you have. So I've had a great time testing out the Pixel 2 camera. But enough of that, let's go into devices and hardware. So in the last few years in the smartphone market, every year has brought massive innovation in hardware. Things like performance, network speed, or battery life. That's enabled all kinds of new experiences like mobile gaming and YouTube streaming. But these days, all premium smartphones kind of look and feel the same. They have the same shape and size, the same displays, and the same processors. And if you've gone to buy a new phone recently, you probably picked it up and it probably doesn't feel much different than the phone. It turns out that pure hardware innovation is largely over. Luckily, there's a lot of innovation left if you look at the intersection between AI and software with hardware. It's not just true of phones. I'm going to go through a couple examples, and then we're going to come back to pixel photography. So the first example is Google Home. Our customers can purchase Google Home and place it in a room, and then they can talk to it. They can ask it things like, what's the weather today? Or they can say, set a timer for 10 minutes for noodles. Or they can even ask it, what sound does a cow make? And by the way, that last one is really good with kids. The great thing about Google Home is no matter where you're standing in the room when you talk to it, or no matter how loud or crowded that room is, it can always hear you. It can always pick out your voice. And the way it does that is by locating your voice very precisely in that room, tuning in on you, and tuning everything else out. When we thought about how to do that originally, we planned to have 8 microphones on Google Home, arranged in a circle. And by timing when each sound hit one microphone versus another, we can determine the location of that sound. But we also experimented with something called neural beamforming. This is a deep learning-based approach to do the same thing, to locate the specific source of a sound. And we found that with neural beamforming, we could do the same thing, but with 2 mics instead of 8. And that's why our customers, when they buy Google Home now, Google Home only has 2 microphones. We found that we just didn't need that many. And this is the kind of thing that's possible when you build hardware together with the software and machine learning capabilities. It's really made better with AI. So I'll take another example from our Google Home line of products. This is Google Home Max. Customers can do all the same things with Google Home Max that they do with Google Home, ask it questions, things like that. But Google Home Max is also a high-end speaker. It's really designed for people who love music and want to listen to music in their own homes the way it would sound when it was originally mixed by the artist. The challenge with buying and using high-end speakers today, though, is they were always tuned to sound good in ideal conditions. When you mix audio, you do it in a studio, and audio sounds really good there. And when you take it home, it doesn't quite sound as good. It turns out that the audio quality of a speaker depends really strongly on things like where in your room it's located, a corner or against a wall, and even on the size and shape and the kind of furniture and fabrics that you have in your room. With Google Home Max, we use a machine learning algorithm that was trained on thousands of different kinds of rooms to see how those rooms affect audio quality. And then Google Home Max dynamically rebalances its audio characteristics to sound really, really good in our customer's specific room. This is an example of how we can take a problem that's historically unsolved and solve it using AI and machine learning. Get something that's really tailored to our customers and their homes. Okay, but I wouldn't be the Pixel photography PM if I didn't talk about cameras. I am kind of a photo geek, so I've been wandering around Tokyo for 3 days, taking pictures with 2 cameras, not just one. One is my Pixel, or my Pixel 2 smartphone, and the other one is a big, more flexible camera, a DSLR. And what's on the screen behind me is roughly the same picture, one on my Pixel and one on my DSLR. And at first glance, they look really, really similar, kind of crazy similar. The key thing is that blur that you see in the background on the right side of the image. That blur is really, really important for a portrait because it takes the viewer's eyes on the subject, the person, the thing that really matters, and prevents them from getting distracted by what's going on in the background. That blur is kind of a side effect of using a really big camera because you have these big glass lens elements that focus some light really well and the rest of the light not so much. But it's really hard on a smartphone because we don't have those big glass elements. And if you look at what the Pixel picture looked like before we applied all that software to do the blur, you can see that it's sharp all the way from front to back. And you really need that software to make it look blurred in the background like you would get with a big camera. What we need on Pixel is an algorithm. It can understand what's close to the camera and what's far away. And then we can kind of fake the blur based on those distances. So if you think about how you would do this as a human being, well, you have 2 eyes, and your 2 eyes give you a left and a right view, and that's responsible for your sense of depth perception. And that's what we need on Pixel. Well, Pixel 2 kind of has 2 eyes as well. It has a special image sensor. On most image sensors, each pixel is a square. But on Pixel 2, we split that square into 2 left and right subpixels that are each a little rectangle. When we take a picture, we take all the left pixels and all the right pixels, and we end up getting 2 images of the same instant, one through the left side of the lens and one through the right. It's having 2 different views of the same world through 2 sides of a very, very small single camera. Once we have those 2 views, we can generate a rough depth map, which shows what's close and what's far. This is a really challenging problem because the software has to account for all kinds of minute hardware differences, variations, noise, lens shading, irregularities, and so on. And even if we account for all of those issues, you still end up with a depth map that's incomplete and imperfect. It turns out even your human eyes can't make a great depth map. Your brain has to make all kinds of educated guesses about the distances to things that your eyes can't discern by themselves. And portrait mode has to make some guesses as well. We make those guesses using machine learning. We generate what's called a segmentation mask. A machine learning algorithm looks at every pixel in the image and determines whether it's part of the person, so not blurred, or part of the background, blurred. We use a convolutional neural network to do this. And it's really important to train it well because not all scenes are as simple as a person in a background. There are also big hats, fuzzy scarves, glasses, earrings, and maybe your hair is blowing in the wind. And portrait mode needs to do the right thing in all of those cases as well. And to do that, we trained this segmentation algorithm on almost 1 million images with all kinds of people, clothing, and backgrounds. Once we have both the segmentation mask and this rough depth map, we combine them together into a single, highly refined depth map. And then, now that we know the distances to every point in the image, we can fake the blur based on that. Things that are closer have less blur, things that are further have more blur. And so you can see in this image, the background is sharp in the original and blurred in the portrait. Like all the examples I showed you earlier, this is something that's made possible only because of the applications of machine learning and AI and their tight integration into the camera hardware beneath. And as you can see, I've had a really great time taking probably way too many portrait selfies in Tokyo over the weekend. And this trend of integrating software and AI with hardware is true in all of our products, not just Google Home and Google Pixel like I've talked about. These are just a few of the incredible capabilities that exist in Google hardware today. And now I'll ask Lynn to come up to talk about all the hard work we're doing to let everyone talk to their computers.
Thank you, Isaac. Hello, my name is Lynn Ha. I'm a director of research programs based out of New York. I lead teams around the world working on applications of artificial intelligence for linguistic problems. I like to say that we teach machines to understand humans. And to that end, human language is really natural language. And so we're working on Google's ability to build natural language systems. So let me start with a story about, in Thailand, about a boy named ran away from home when he was 7 years old, never getting an education, but survived about 15 years doing manual labor. Went into an internet cafe, and though he didn't know how to type, he saw the microphone icon on a Google web page and spoke into it with it using in Thai and spoke his name. And the search result showed that he was actually listed as a missing child with the Mirror Foundation. And this allowed him to be reunited with his family. On's story helps us illustrate the very personal, on a very personal level, the importance of Google's mission of organizing the world's information and making it universally accessible and useful. Language is critical. Our ability to process language, understand language of the world is important for that access. With AI, I like to say that we're modeling the world. This is both exciting and challenging. There are over 6,000 languages spoken. Think about it, 6,000 languages, right? 400 languages of at least 1 million speakers. And then we have lots of dialects. Basically, over 50% of languages that we have listed here are actually dialects. What is the challenge? The challenge is that basically dialects do not necessarily have written representation, and we can't train systems without text, right? But bringing all languages online is a huge task that's very important and something that's very close to my heart. We live in exciting times right now. Smartphones have allowed us to bring more internet users online, but web content has not caught up. Over 50% of the internet is actually in English. And if you think about a language like Hindi, which would represent about the number 4 language in terms of the number of speakers in the world, it's actually just barely the top 30 online with as far as internet content goes. So this is really important. for us to tackle, right? We really want data diversity in order to be able to model the world, as I was saying earlier. So bringing people online is critical, not only because data diversity to represent what the world actually is in the real world to what we want it to be online. Obviously, that's really important. But language is also an integral part of our identity, right? I mean, just in this room alone, imagine how many languages that we speak, right? We want to be able to create, Google wants to be able to create technology and infrastructure to be able to scale the technology and bring more people online so that they themselves are creating content and developing and creating apps. And that becomes a virtuous cycle. But there are multiple steps in bringing a language online, and there are just a couple that I want to talk about that's actually quite challenging, that we often take for granted because many of us are speakers of English or something that is more of a priority, if you will, as far as web pages go. So Unicode, that's the first critical step. Unicode is the ability to encode and represent scripts, right? So we want to be able to have every character and every script with a unique number assigned to it. Now, the challenge here is that when you think about a country like Myanmar, where you have technology that's rapidly growing within that community, they've created their own version, which is a non-Unicode version called Zaji. Zaji is really challenging because once non-Unicode and inconsistent standards have been developed, and each developer is creating their own version of their font, if you will, it creates a situation where a husband and a wife sitting in the same room using the same phone can't actually communicate with each other, right? So Google works very closely with the Unicode Consortium to figure out how we can, as an industry, solve this problem. The other big step here is, I mean, we just talked about the importance of Unicode and having consistency. But the other really important factor is actually fonts. We take for granted, I mean, if you think about back in the ages of graphic design and the different kinds of true type and fonts and systems, now we're in an era of mobile phones, right? But for having fonts to be able to display and represent the Unicode that we just talked about is actually also really important, not just for desktops, but also for mobile phones, right? So we need to have enough fonts to be able to represent all the scripts of the world. So Google has actually open sourced Nodo fonts, about 800, in over 800 languages and 110,000 characters. Nodo, by the way, means no tofu, and that is the sort of little white square you would see if you don't have proper representation. So we talked about encoding, we talked about fonts, and then the next obvious thing is input. Once we get all of this displayed and represented, how are people going to actually enter data, right? So one of the big critical steps, obviously, is keyboards. But the thing is that we take, again, in English for granted in that there are 26 characters. But imagine a language like Khmer, which has 70 characters. And how are you going to actually display that on a keyboard? This is really challenging. And this is something that we've used machine learning to be able to create keyboards to be able to predict words and make that a whole lot easier. The other difficulty here is, okay, we just talked about keyboards and how difficult it is. And if you think about a smartphone and the screen real estate for keyboards, the obvious natural thing to do with some of these scripts is actually to write it in, right? To be able to draw in write in the way you naturally would with a pen or with your finger. And so Google has actually used machine learning to be able to do character recognition in different handwriting patterns to launch and display over 97 languages. So we talked about input for keyboards, we talked about input for handwriting, but you know, we're all talking about phones, and the most natural thing to do with a phone is actually to speak into it. So to be able to go and have the speech recognition system going was something that we really wanted to try. But you'd be surprised, but back in the old days of speech recognition, the way data was collected was for somebody to call on a landline and answer specific prompts. That didn't create enough data, and it was very expensive, especially for the kinds of queries that we're interested in now. So we experimented with what we call Google 411, where we had people call in to ask for business listings, business telephone numbers. And that gave us enough data in English to be able to launch our very first voice search model. right? But as I was saying earlier, we can build models for English, but what we really want is more than English. So to go beyond English, the traditional method would have been to buy that data. But the data actually is not available for all languages. The data for some of these languages, like for Cantonese, for instance, is much more difficult. So I went around the world and every time, so as an international program manager, one of the challenges would be I would go to a new location and people would say, "Oh, Lynn, by the way, do you think you could fix this thing for me? Because I really like using this product, but it's not really working well for my language." And I thought, what better way for us to actually be able to build a model for a language than to the very people who are going to be using our system, right? So in order to be able to launch voice search in Dutch, we experimented with a crowdsourcing program, which is, let's go to the people who we know are big fans of Google, give them some phones, and have them reach out to their friends and family to be able to collect this data for their languages. And it was a huge hit. It worked really well because not only were we able to get the data of the voice samples and the diversity of accents and dialects, but we were also able to collect acoustic data, the different environments in which most likely people will be using their smartphones. And that was really critical. This allowed us to basically launch about 50 languages within 3 years. And this is all with the help of people who were really avid users of Google products who wanted to make sure that voice search worked in their language. So basically in 2012, we were able to go even a step further using neural nets to improve our speech recognition system. In English, we improved it by over 25%. One of the really interesting aspects here is that when we think about language and we think about sounds, and as I said, the different sort of acoustic value to an environment, it's really hard sometimes for a machine to understand the difference between a language, a human sound, and a non-human sound. So deep neural nets allowed us to actually be able to process that and improve like sound recognition, actually. So in 2017, we've been able to actually launch 30 more languages, and we have about 119 language varieties available. And we have 11 Indian languages, 3 Indonesian, and 2 of the Africa's popular languages of Swahili and Amharic. So we just talked about speech recognition, and if you think about speech recognition, that is the ear of the machine. But you know what would happen is that we would do the speech recognition where somebody would query into the phone, but the result was basically a web page. So if you said, "What is the weather in Tokyo?" you would just get a little list or a weather icon. But once again, we had a phone. We wanted to be able to speak to it and have the phone to be able to speak back. And again, the traditional method of actually going and building a TTS system is really to be able to buy this data or to go into a professional studio, because as opposed to speech recognition where you wanted to have the diversity of speakers, the diversity of acoustic environments, for a TTS system, the data that you wanted was actually one perfect speaker, a professional, basically, who knew how to do this. You had a really great studio, and a sound director and a sound engineer. So it required at least 4 people and probably 3 to 6 months of recording time. You can imagine how much that would cost, right? So for languages, which I was really interested in, the low resource languages, we wanted to figure out how can we do this? Because we just learned from the word of mouth for speech recognition, how can we crowdsource this information, right? How can we crowdsource this process? And I remember I was watching a comedy show where basically you had these comedians impersonating a politician. And I thought, oh, that's really interesting how different people could have the same vocal profile. Or I could hear somebody and I could think that that person sounds exactly like so-and-so. And so I thought, why not try to get people who had similar vocal profiles? And what we did was that we basically got let me get to the next part. We basically got the technology of a laptop without a fan, which was critical for us to be able to do this, and find people who had similar vocal profiles and a really expensive and good mic. The mic is critical here. With that, we were able to actually go create a traveling booth, and do samples. So we created an app, a web app called ChitChat, and then we experimented, and basically using parametric synthesis LSTMs to develop parametric synthesis, we only really needed 2,000 lines compared to what we've done before, right? So and all of this cost under $2,000. And that allowed us to create a sample that was pretty decent, okay? And basically what we did was we wanted to experiment with this before we went out into the world, and we got Bangladeshi Googlers, about 15 of them who auditioned. They each spoke about 45 minutes, and we got 2,000 phrases in Bangla and English. And then we had the wider community vote to decide which voice they liked the best. So the whole process is a neural nets model to be able to actually find the average voice. Because the truth of it is that the truth of it is that if we did a fantastic job, we would actually have a voice that sounded like a living, breathing person, right? And that becomes a problem because if your phone or your GPS sounds like another person that's actually living and walking around the world, that's not perfect. What we wanted was a human sounding voice, but not necessarily a voice that sounded exactly like a person, right? So this allowed us to create an average voice, where with the 10 speakers, we created an average voice, and let me just show you what it sounds like here. Here we go. Where is the...
Shaguto.
I don't know if anybody speaks Bengali here, but basically that voice was created by volunteers, and we were able to launch this. And the other thing is, because it's inexpensive, we got to do male and female voices, and all the data that we collected, we open sourced and made it available to developers as well. So we have launched Bengali, Khmer, Nepalese, Sinhala, Javanese, and Sundanese. Javanese and Sundanese is really interesting. It's actually launching today. That's really interesting because we decided to do the next step in Project Unison. So I just talked to you about multi-speaker. What about multilingual, right? Why not, instead of an average voice, why not a uniform model, right? So we think about how, one example is, for instance, like in India, where many people are trilingual. And many people here are bilingual. Why not reuse the sounds that you create in one language for the other? Why create a single model each time, right? So with this next step is that we were able to blend in Javanese and Sundanese voices that we've just launched today were actually blended. They're combined with Indonesian, Bahasa Indonesian, and we found out that actually gave us a higher quality score than building single language models. So this allowed us to think about how dialects could happen. Dialects, we've launched actually Singaporean English in the Assistant recently, and this was using the same Unison project of multi-speakers donating their voice samples. And basically, one of the most important parts here is that, as I said, dialects are the next step. Dialects are not necessarily written, are not represented in written form, but the information is critical, right? How do you actually decide whether you have English or Singlish if you're only reading English and processing and developing models that way, right? How are you going to be able to emphasize or hear the emphasis and understand where prosody happens if you only use text? You need to be able to actually go to the acoustic, to the data. And that's the next step that we're working on, to be able to build dialects so that you have, not only are you speaking to the machine in your own unique dialect and your own unique accent, what you get back is the same, right? The entrainment. It's really important for us to be able to have a system that allows us to speak in your own language in your own accent, not only to be able to understand this, but also to generate and respond in kind. So the importance of voice, as with the story that I started with, we really want to have more people access information, and so voice allows non-literate users. The second thing is, how do we get this enabled in all the different apps, right? And the third is ubiquitous computing. You want to be able to walk into a room and to be able to talk to it and not have to type in something, but do something natural. That interaction that we as humans have with each other is communicating with speech and with voice. It's not typing into a keyboard to talk to the next person, right? So basically, voice and the development of voice for all these languages will take that one step further. So thank you very much for your time. Next, I want to introduce Prabir, who will talk to you about the Google Assistant.
Google. Hey Google.
Hey Google.
Okay, Google.
Hey Google. Play some dance music.
Sure. This is fresh air. My guest will be
Kimmy Schmidt on Netflix.
Okay, Google, count to 100.
Sure. 1, 2, 3.
Play vacuum harmonica on my TV.
71, 72, 73. Play the Wonder Woman trailer.
Hey Google, talk to Dominus.
Talk to Lonely Planet.
Talk to Cora.
Show me my photos from last weekend.
Your car is parked at 22B. Today in the news.
Turn the living room lights on.
Okay, turning on the lights.
I'm back, baby.
Hey Google, drop a beat.
Flip a coin. Call Jill.
Set a timer. Talk to Headspace.
And then just for a moment, I'd like you to let go of any focus at all. Just let your mind do whatever it wants to do.
Done.
Hey Google, good night.
Turning off all the things. See you tomorrow.
Hi everyone, my name is Pravir Gupta. I am Director of Engineering working on the Google Assistant. I'm pleased to be here in Tokyo to talk about something that we are really excited about. How machine learning is allowing us to build completely new products like the Google Assistant that you just saw in the video, which helps you get things done in your daily life. Before I dive into showing you the Assistant, let me take a quick step back and explain what makes the Assistant possible and how we got started. We first introduced the Assistant a little over a year ago. And from the start, we have said that the Assistant is a conversational experience between you and Google that helps you get things done in your world. The Assistant is built on the evolution of a number of Google products, from search to maps to calendar and photos. And thanks to Google's experience in machine learning, contextual understanding, and speech recognition, you can have a natural conversation with Google Assistant. So what does that mean? We truly believe that the Google Assistant should be the easiest way to accomplish any task, and that is through a conversation, something that comes naturally to many of us. With the Assistant, you can ask a question, and the Assistant answers. Seems simple, but the conversation does not just happen by voice. You can seamlessly switch from voice to typing to tapping, often in the same conversation, selecting what's most efficient for the task that you're trying to accomplish and the type of device you're on. In trying to answer and help you get things done, there's a lot that happens behind the scenes. Let me show you with an example. Let's switch to the phone, please. So my flight landed in Tokyo on Sunday, and yesterday I was exploring a few restaurants, and I was wondering if I need to tip in Japan or not. Let's ask the Assistant. Should I tip in Japan?
According to TripAdvisor, tipping in Japan is not mandatory. It could be said that tipping is not a common practice in Japan. In many cases, maybe most tips may be politely refused. If you do attempt to tip someone, there may be some confusion.
So let's switch back. So it seems simple and pretty straightforward. but actually there's a lot of machine learning that's actually working behind the scenes. First, the assistant has to understand the question that you're trying to ask. We just heard from Lynn Haas talk about the steps involved in natural language processing. Secondly, the assistant has to find the relevant information from thousands of web pages and read back only the part that you care about. It's not just finding the right web result. And thanks to machine learning and natural language processing, the assistant helps answer these seemingly simple questions. It's only made possible with AI. We want the assistant to be available wherever you need help. From your morning commute to your kitchen, from your morning commute to your kitchen, to your errands around town. The assistant should be able to help you in a smooth and connected way. Since many of the folks in the audience are from different countries, I just want to cover some of the basics. The assistant is available across many devices in various languages and countries. The assistant is available on eligible Android phones, on iPhones, speakers like Google Home, Android Wear, Android TV, and more. The assistant is ready to answer all kinds of questions and provide help throughout various tasks during the day. The assistant also works with third parties based on the actions on Google platform, with actions like Woolsworth in Australia or Pikachu Talk in Japan. So let's move on to a more risky part of my demo. And this will be kind of fun for all of you. So these are all live demos, and I'll continue showing the assistant on the phone. Let's switch to the phone, please. Hi, how are you doing, Google?
I'm great. Thanks for asking. Anything I can help with?
Can you please tell me how's the weather tomorrow in Tokyo?
Tokyo tomorrow, it'll be clear with clouds from time to time, with a high of 19 and a low of 7 degrees Celsius.
How about on the weekend? So notice that I'm using natural language and not keywords. And because of machine learning, the assistant is still able to understand easily. As I mentioned, my flight landed on Sunday, and on the flight there were lots of movies. I was wondering if there was one that was shot in Tokyo. Let's ask the assistant. Oh, casting ended. Let me try and fix that. Oh no, Wi-Fi disconnected. Okay, I give another try. It says connected to high. I promise you there are lots of demos and it gets interesting. So let's give it a few minutes. Oh no, he's running in the back. That can't be good. Let me try disconnecting and connecting again as well. Sorry. Yeah. Don't see him coming back, so why don't I proceed and then we can come back to some of the demos. So in the Asia Pacific region, the assistant is already available in many countries and languages. But we are not done yet. We are continuously looking to add more devices and more languages for the assistant. Our goal is to make the assistant available to whoever needs help. Okay, now it's casting. Okay, maybe the Wi-Fi is back. Let me go back to the demos and I'll come back. All right, perfect. So I was telling you, my flight landed on Sunday, and on the flight there were lots of movies, and I was wondering if there was a movie that was shot in Tokyo. Let's ask the assistant. Can you show me what famous movies are shot in Tokyo?
Movies frequently mentioned on the web include Lost in Translation, The Fast and the Furious, Tokyo Drift, Adrift in Tokyo, and others.
It's great to see the Fast and the Furious Tokyo Drift here. As you'll note, the assistant was easily able to understand a natural language way of talking about movies using expressions like shot in Tokyo. These were just some examples of asking for answers and getting answers, but the Google Assistant is a personal assistant. It should be able to help me with things that are personal to me. So let me show you some things. When is my flight to San Francisco?
Flight is United Flight 876 to San Francisco, which leaves tomorrow at 25 p.m.
How is my team doing?
United FC are second in the Premier League.
Now you all know my favorite team. The way this works is because I've told the assistant, what's my favorite team?
Me that you like Manchester United.
So this is the new type of interaction where you can teach the assistant and it remembers things. The Google Assistant is a conversation with all of Google, and it can help you connect with different apps, like Google Photos. Let's try that. Show me pictures of Anish. So Anish is my 4-year-old son.
Look at these pictures from your Google Photos.
Isn't he cute? So Anish is also a common Indian name, but the Google Assistant knew that I was not looking for pictures of any Anish in the world, but I was looking for pictures of my son Anish. This is made possible with machine learning. So recently, Manchester United were also playing a game in San Francisco, and both Anish and I got to go through the stadium to see the game. Let's try to find that picture. Pictures of Anish in a stadium.
Look at these pictures from your Google Photos.
Okay, so before I move back to the slides, let me show you one more thing. Tell me a fun fact about Tokyo.
To Wikipedia, an Akita named Hachiko waited for his owner at the train station every evening for almost 10 years after his owner died. A very good dog.
Quite a loyal dog. So hearing the dog bark, if you're from Australia, you'll find this one quite entertaining. What sound does a kookaburra make?
Kookaburra sounds like this.
My kids are always having a blast with animal sounds. Besides providing answers and helping you get things done, the assistant also has a personality and can keep you entertained. Now I think I'll need some help before I switch to the slides. So let's try this. Help me speak Japanese.
Opening Google Translate.
Please switch to presentation.
プレゼンテーションに切り替えてください。
And if somebody understood Japanese, let's switch to the presentation. Perfect. So as I was saying earlier, in the Asia Pacific region, the assistant is already available in many countries and languages, but we are not done yet. We are continuously looking to add more devices and languages to the assistant. Our goal is to make the assistant available to anyone who needs help. but it's really important that we strike the right balance between making the assistant helpful and ensuring that the assistant understands you. We are working hard and looking forward to make the assistant available in more locations in the upcoming year. So that was the Google Assistant, powered by machine learning, a personal way to get things done in your daily life. And we can't wait to continue to make the assistant more available and more helpful over the coming year. Thank you.
네, 감사합니다. 다음 세션 전까지 5분 정도 휴식 시간을 가질 예정으로 화장실 다녀오신 분들께서는 그러시고 밖에서 음료나 간식 같은 것도 가져가시면 되겠습니다.
The services. Our product team is constantly expanding the product suite. There are two major ways we support the businesses with AI tools. First, we offer open source ML platform called TensorFlow. Second, we offer Google's machine learning abilities through pre-trained ML APIs such as Speech API or Vision API that businesses can plug right into their software. Let me start with TensorFlow. As you have heard from Jeff, in 2015, we launched TensorFlow, a framework developed by Google for creating deep learning models. TensorFlow simplifies the deployment of large-scale machine learning models. It can run on computers of many kinds, from GPUs on the cloud or small CPUs on small devices such as smartphones or embedded systems. It's been exciting to see what businesses and researchers are using it for. You'll see some great examples from the world of science later on when we talk about health and the environment. For providing an even better development environment for TensorFlow, we built our own custom hardware for running machine learning models called Tensor Processing Unit, or TPU. TPU is a custom chip designed specifically for running machine learning models. TPUs enable businesses and researchers to train and run cutting-edge machine learning models at faster speed and larger scale. And TPUs can reduce the cost of machine learning work and speed up time to market for new AI applications. Secondly, we offer pre-trained machine learning APIs that allows businesses to plug and play Google's machine learning abilities right into their software. Let's see some examples of these APIs. Cloud Vision API. This API helps understand the content of images using powerful machine learning models that quickly classifies images into thousands of categories. We also have the Video Intelligence API, which makes video searchable and discoverable by extracting metadata. Businesses can now search every moment of every video file in your catalog and find every occurrence of something as well as in its significance. Cloud Speech API, it converts audio to text. It recognizes over 110 languages and variants. Businesses use this to transcribe text of users dictating to an application's microphone, or let workers command programs through their voices, or transcribe audio files. Cloud Translate API is an interface that can take any string of text and translate it into another language using neural machine translation technologies Jeff talked about earlier. Cloud Natural Language API reveals the structure and meaning of text. Businesses use it to understand sentiment about their products on social media or understand intent from customers' conversations happening in the call center or messaging app. As you see with these APIs, AI has a promise to help transform businesses across many different industries. We are hoping that cloud ML tools will help more and more businesses innovate to create new businesses, optimize their processes, and take business to the next level. Now I'm very happy to introduce Takeshi Ogino-san from the famous Japanese company Kewpie, who is an innovator in using our TensorFlow. He will be showing us how machine learning has changed Kewpie's business. Please put your headset on for translation to English. Please.
Thank you for introducing me, Sato-san. And my name is Takeshi Ogino, in charge of next generation technology, working for the Kewpie. But I'm afraid that I'm not good at English, speaking English. So please allow me to speak in Japanese from now. はい。それでは日本語でお話しさせていただきます。ここですね。すみません。まずですね、キューピーですが、1919年、中島東一郎という創始者がですね、作った会社でございます。で、その時ですね、やっぱり日本人の栄養不足、これを解消したいという志のもとに作られた会社で、現在約5500億円の売上規模の食品会社となっております。キューピーはですね、来年、再来年で100周年を迎えますけれども、今回ですね、栄ある日本で安全安心のブランドでナンバーワンをいただきました。で、調査会社の調査によりますと、これは理念に基づく現場力と言われています。キューピーの強みは、この理念に基づく現場力ということになります。キューピーもですね、昨年夏頃より AI によるイノベーションを検討しております。このイノベーションということはいろいろ定義がございますけれども、一番最初に定義づけたのはシュンペーターですね。で、シュンペーターはイノベーションは新結合という定義づけをされていました。一種のものを結合させて新しい飛躍的な価値を創造するという意味です。私どもキューピーはAI に現場力、強い現場力を掛け合わせてより良い価値を創造する。そのために企業価値を強くするということを考えております。この企業価値、これもいろいろな定義がございますけれども、私どもはお客さんの声をお客さんの価値に変換する力と考えております。この企業価値も縦軸のエンジニアリングチェーンと横軸のサプライチェーンですね。いわゆるバリューチェーンからなっております。それぞれのバリューチェーンに AI を掛け合わせて最高のお客様の価値を創造する。このために AI を使うというものでございます。じゃあ AI はですね、どういうものでしょう。定義がですね、いろいろあると思います。学術界を調べますと、定義というのは実はきちっとした定義がないんですね。で、私ども使う側から見たら AI について考えてみたいと思います。我々人は知力と体力から構成されています。体力を機械化するのがロボット、知力を機械化するのが AI と考えています。この AI によって知的作業を活字に省力化してさらにスピードアップさせる。このように我々は考えております。ただですね、人には知力と体力ではないものがあります。機械化できないものがあります。これが心ですね。心。特に人のため、あるいは社会のために貢献するという心。これは目的を持つ心、志と言いますが、この志というのは AI でも機械できないものと考えております。私どもですね、この AI を使う時の志、これは先ほど申し上げた現場力に AI を掛け合わせて企業力を強化してより良いお客様への価値を提供する、このように考えております。ところで今まで AI と申し上げましたけど、本当に AI って使い物になるんでしょうか。これはいろんな企業さんでもいろいろと議論されていると思いますし、私どもも去年いろいろ議論させていただきましたが、正直やってみないとわからないというのが正直なところです。それじゃあやってみようということで、去年の夏頃からですね、いろいろ検討を始めました。そして 闇雲ではなくてですね、その時の技術、今の技術ですね、今の技術でも解決できない現場の課題、ここにいくつか挙げておりますけども、これに AI を掛け合わせて価値を創造していく、このように考えております。今日はですね、時間も限りがございますので、一番上のですね、原料検査装置について、もう少しお話をさせております。また理念に戻りますけども、キューピーにおきまして、昔より、創業時よりですね、伝えてこられた、大切な考えがあります。これは、良い商品は良い原料からしか生まれないという教えです。我々キューピーですね、食品メーカーで原料を非常に大切にする会社ということです。でですね、まず AI を使うときにですね、原料検査装置、この対象としまして、一番安全安心が重要とされているベビーフードを対象にしております。ここに使われてますライスポテト、これは1センチ角ぐらいにかけられたポテトなんですけれども、これの検査、これに適用することを考えました。ここにですね、ポテトの実際の写真がありますけど、どこにその不良があるかっていうのは分かりますでしょうか。これパッと見てなかなか難しいと思うんですけど、実はここに実は不良があります。不良と申しましてもですね、実はこれは我々信頼できる原料メーカーからいただいてますので、全く安全なものです。安全なものです。食べても無害です。ただですね、ベビーフードでお母さんが赤ちゃんにベビーフードをあげるとき、黒ずんでいたりするとですね、心配になります。これって本当大丈夫なのかな、そういう心配不安をなくす、安心を提供するためですね、これは人が一個一個全部チェックをして、品位の悪いものを取り除くという作業を現在しております。これ非常に大変な作業なんですね。1日1人で100万個以上、多い時は数百万個を確認するわけです。これ非常に大変な作業です。キューピーにはですね、人への優しさというのを重要視する企業風土がございます。このためですね、いろんな機械化というのを試みてきたわけですけども、現実には難しいというような結論でした。その時ですね、苦しい時の神頼みじゃないですけども、AI でできないのかなということで検討しました。これ AI やってる企業さんいっぱいおられますけども、我々も正直20数社ぐらいですか、ベンチマークさせていただいて、いろんな要件項目からやはりこれは Google のTensorFlowプラットフォームが一番ベストだという結論に至って、ここ六本木ですねに相談に来させていただきました。それでそこでですね、Google のパートナーであるブレインパッドさんもご紹介いただいて、そこで協業を始めたわけです。でですね、協業を始めてですね、2ヶ月ぐらいですか、TensorFlow上でいろんなアルゴリズムを検討してですね、2ヶ月ぐらいで、これはいけるっていうアルゴリズムが分かりました。でこれはですね、今まで不良品を登録して検査をしていたんですけども、そうではなくて逆転の発想ですね。いいものを AI が学習をして、いいものを見つけ出す。それ以外のものは不良品っていう考え方です。ですから不良品を検査するという直接的なものではなくて、良品を検査をして、それ以外を不良品としてみなすというアルゴリズムです。でそのためですね、AI に、TensorFlowの上のアルゴリズムに AI にですね、最大100万個ぐらいのポテトを学習をさせ、これは良品のポテトですねを学習させて、その後で検査工程でそれを使って良品を確認して、それ以外を不良品とするというものでございます。でこれこれいけるなっていう考えで去年12月ですね、こういうのでいけるよねっていうのでポンチ絵を書いて、この2ヶ月後ですね、これブレンパードさん、Google さんおよび我々のエンジニアですね、2ヶ月後にプロタイプっていうのはもう出来上がりました。でこのプロットですね、の動作なんですけども、 ベルトコンベヤー流れてるのはこのカメラで見ていて、その AI が判断していって、不良があると、今はこれ音が鳴って、座標に合わせて音が鳴るように仕掛けてるんですけど、今のシステムはその座標軸を持ってベルトコンベヤーのスピードを計算をして回収するというところまで今来ております。でこれ最近ですね、これ、工場に入れて、一緒にですね現場のものとブラッシュアップをしている、写真ですけれども、当然 AI だけではこれシステムはできないんですよね。で食品メーカーですから、その機械の安全性、衛生面等々ですね、いろんなものを現場の目で見て、どんどん今ブラッシュアップをして完成に近づけているんです。このようにですね、かなり時間をかけてもできなかったものが短期間で実現したと。これは非常に手前味噌な言い方ですけども、弊社のキューピーの現場力、強い現場力に世界一強い AI を持っている Google とブレインパッドの力、これを掛け合わすことによって実現できたものと考えております。それでですね、これは我々現場の中のこういう省力化だけではなくてですね、この考え方、このシステムをキューピーだけではなくて、原料のサプライヤーさん、そしてコンピューターかもしれないですが、食品メーカーさん、そして全世界のサプライヤー、食品メーカーさんにもお使いいただけるようにしたいと考えております。でですね、最後になりますけれども、AI というのはまだですね、我々から見ても、まだ赤ん坊、まだ未熟なところあると思います。使っていて正直苦労することもあります。ただしですね、無限の可能性があると思っています。この無限の可能性を引き出すのは企業力であり、現場力。そしてそれを実現させるのはですね、人ではなくて、すいません、間違えました。AI ではなくて、これは人が持っている志、これを実現したいという志ですね。志と、それを実現させるための良きパートナーと思います。はい、ご清聴いただきありがとうございました。以上で終わります。ありがとうございます。
My name is Boo. I am a high school student, 17 years old. People learn in different ways. For me, if I see something really cool, I'll try to take it apart and figure out how it works. It's a bit more extreme now because instead of it being hardware, I like to know how algorithms work. My freshman year, I remember Googling machine learning. I had no clue what it meant. That's the really cool thing about the internet is that someone's already doing it, so you can just YouTube it and it's right there. The minute I really saw what machine learning can do, it kind of like hit something within me, this like need to build things to help people. My parents are immigrants from Afghanistan. It's not easy coming in. The only reason we made it through some of the times that we did was because people showed acts of kindness. Seeing that at an early age was enough for me to understand that helping people always comes back to you.
Machine learning is this concept that we can train computers to identify patterns in data and then use those patterns to predict off of new data. I have a quick demo. It's just some code that I wrote last night.
Miss Roscoe is the first teacher that I actually talked to about machine learning.
Abu and I first met his sophomore year. I was his Programming 1 teacher. My students do a computer science fair, and they are challenged to find a problem, but they have to use a form of technology to solve that problem.
And then it kind of hit me in a way where I could actually genuinely help people. Mammograms are the cheapest imaging format there is. It's the most accessible to people all around the world. But one of the biggest problems that we see in breast cancer is misdiagnosis. So I decided that that was going to be my project, build a system for early detection of breast cancer tumors that's accessible to everyone and that's more accurate. How was I going to do it? machine learning. It's not an easy thing to do. Data is not publicly available, and if it is, it's low quality data. It's difficult. I wasn't even sure if I could do it. And I remember just thinking about like, everyone else is building a calendar, like maybe I should do that. But I was like, no, you gotta do this. You need to.
He was talking to me about all the cool stuff he was doing, and I was telling him not to overdo it. You should just be a kid and worry about kid stuff.
The biggest, most extensive resource that I've used is this platform called TensorFlow. I've spent so many hours going really deep into these open source libraries and just figuring out how it works. Eventually, I wrote a whole system that can help radiologists make their decisions. All right, ready? Yeah. I'm by no means a wizard at machine learning. I'm completely self-taught. I'm in high school. I YouTubed and just found my way through it. You don't know about that kid in Brazil that might have a groundbreaking idea, or that kid in Somalia. You don't know that they have these ideas, but if you can open source your tools, you can give them a little bit of hope that they can actually conquer what they're thinking of.
Hi, everybody. My name is Lily Peng. I am a doctor by training, and at Google, my team applies deep learning to healthcare, and specifically medical imaging. So the story of Abu that you just saw is incredibly inspiring. One, because he is, after all, a high school student, but two, it's an example of the potential that this fairly new technology, deep learning, can bring to an old problem like healthcare. And in fact, if you look at the number of papers that feature deep learning in medicine, this number has increased 20-fold since 2013. And this rapid pace of discovery is just the beginning. And of course, this is not just healthcare. Machine learning also promises in breakthroughs in a lot of other scientific areas. So today, I will give you a few examples, in three areas. One in environmental conservation, one in energy consumption, and the last one in healthcare. So let's start with an example in environmental conservation. So this is a picture of a sea cow. He's really cute, but sea cows are also, unfortunately, under the threat of extinction. Now, in order to protect these animals' habitats, marine biologists have to be able to track the animals' movements and where they are in the oceans. Now, this is a pretty difficult task, and for decades, scientists would fly in small planes over the ocean to try to do this. Now, a couple of years ago, biologists started using drones to get aerial images to get better coverage. But of course, now they're faced with these type of images, a lot of them. And spotting a sea cow is actually quite difficult to do. So in fact, there is a sea cow in this image. Can anyone see where it is? It's in the lower right. Right there. So it's really hard to find these little shadows in the ocean. And so the breakthrough really came when a group of biologists from Australia teamed up with computer scientists, and they built a TensorFlow model to help find these sea cows automatically, so made findable with AI. And an early version of their detector could find about 80% of the sea cows that they could do manually. Good thing I wasn't doing this, because I would find no sea cows. And these results are very encouraging, and with better tools like these, conservationists have a much better chance at protecting these animals' habitats. So another example I'd like to walk you through is an example of machine learning helping in the area of energy efficiency. So this is a photo of a Google data center. You can tell it's a Google data center because it's very colorful. And large-scale commercial industrial systems like these consume a lot of energy. And for the past decade, we've made reducing energy consumption a priority. But the real breakthrough came when we worked with the DeepMind team to apply machine learning to this problem. So here you see a graph of energy consumption in one of the cooling systems in our data centers. And you can see much less energy is consumed when we turn on the ML algorithm. And so how does this work? Well, we trained a system of neural network on a variety of signals and in the data center, like the temperature, the power usage, the speed of the cooling pumps. And using these signals, we predicted or projected what the energy usage would be like. And with these accurate estimates, this helped us reduce energy consumption in different parts of the data center because we could distribute that consumption much more easily. Of course, the results were pretty fantastic. With machine learning, we were able to reduce the amount of energy consumed by our cooling systems by 40%, and the overall extra energy consumption was reduced by 15%. So this is an example of how we've done this at Google, but you can imagine this type of technology could extend to other complex commercial and industrial systems. Okay, so I've shown you a few examples of how machine learning can help with environmental conservation and energy efficiency. Healthcare, coming back to healthcare, is another huge area where we can really make a difference. So there are two projects I'd like to highlight that our team is working on. One in diabetic retinopathy, so this is diabetic eye disease, and one for cancer biopsies. For all our projects, we really have two goals. One is to build a tool that makes it easier for doctors to find disease. And the second is to encourage more research in this field. So first, diabetic retinopathy. So what is this disease? It's the fastest growing cause of blindness in the world, and all 415 million patients in the world with diabetes are at risk for it. The key to preventing blindness is regular screening, and that's usually once a year. This is done by using a special camera, this one right here, and taking a picture of the back of the eye through the pupil. Then an eye doctor will take these images and grade them on a 5-point scale, all the way from no DR, which is really healthy, to the most severe form, which is proliferative DR. And during grading, the doctors look for little bleeds, so these little things in the eye. Now, this is a pretty obvious picture of lots of bleeding. Sometimes these signs can be quite subtle and it can be hard to find. So the problem is, in many parts of the world, there are simply not enough specialists to do this task. So take India, for example. Here's a picture of people lining up for screening outside of Sankara, one of our partner hospitals. And in India, there is a shortage of 127,000 eye doctors. And as a result of this and other systematic issues, nearly half of the patients suffer some sort of vision loss before they're diagnosed. Now, this should never happen because this disease is completely preventable. So this was a big problem that several eye hospitals had reached out to us to see if we could help. At that time, I worked on the search team. I was helping with health-related searches. And I, along with other folks, saw how machine learning was transforming a lot of our core products. And we thought, well, if we were able to detect dog breeds in images, maybe we could also help with medical images as well. And so a group of us got together and started a side project to start working on this problem. And so you can see some of our team members here. The team has grown a little bit, but when we first started, it was just several people. So we trained a deep neural network to help with this task. First, we had to obtain lots of images, and we got them from our healthcare partners in India and a screening provider in the US. We got in total about 130,000 images to start with. We built a labeling tool and hired 54 American doctors to read the images. They rendered a total about 880,000 diagnoses for the 130,000 images. So in other words, there was some variability in the way that the images were graded, and so a lot of the images were graded somewhere between 3 and 7 times to get an accurate diagnosis. We then took all this data and we used it to train a model. The neural network we use in particular here is called Inception, and it's the same one that's used in photos and other places. It used to classify cats and dogs, and now it's trained to do fundus photos. And after enough training, our model was able to take in an image and give us a 5-point grade. And the graph here shows how our system did for 10,000 images, new images that the model had never seen before. So the black line you see is our algorithm, and the color dots are the American eye doctors. And as you can see, we actually very closely match the performance of the eye doctors. And in fact, if you look at the F-score, which is a different measure of accuracy, our algorithm is just a little bit better than the median ophthalmologist. And of course, we published this work in a medical journal called JAMA, the Journal of the American Medical Association. And publishing is really important part of this. As mentioned, our goal was not only to help build these tools, but also share our learnings with others. And the paper was actually quite well received, and you can see some quotes there from other doctors who read the work. So what's next? Well, the algorithm is currently undergoing clinical validation in hospitals in India and in Thailand. And as another thing that we noticed as we were doing this work was that sometimes getting a high quality image itself was difficult. These cameras are tricky to use, and you have to shoot a picture through your pupil, which is pretty small. So we are partnering with Verily, our sister Alphabet company, as well as Nikon, who makes wonderful cameras called Optos. And we're developing easier to use hardware so that taking the image itself isn't a barrier to screening. Okay, so the second project I'd like to talk about is using machine learning for cancer biopsies. You heard the story about Abu, where he's applying machine learning for mammograms. And mammograms is used for screening people who are at risk for breast cancer. But once you have a positive screen, what doctors will have to do is eventually take a sample of that tumor and look at that tumor under a microscope. Now, this diagnosis is actually quite complex because each of these samples that we take many samples per patient. It's about 10 gigapixels. So that's as many pixels as 1,000 pictures taken with a regular camera. And doctors have to go through these images and look for a very small lesion sometimes. And so this is actually quite time-consuming and difficult. And as a matter of fact, we estimate that this task is so difficult that 1 in 12 breast cancer tests may be misdiagnosed. And that's why we thought, maybe this is, again, a place that we can help. So here on the left, you see a picture of a biopsy of a lymph node. So we started off with a little more straightforward task, which is helping doctors detect breast cancers that had spread to nearby lymph nodes. So here's an image of the lymph node with the cancer cells circled. You can see it's actually quite small. And then we built a heat map model that produces this heat map, so the little red dots there, to highlight and direct the doctor's attention to where there's likely cancer. When we measure model performance, we use a score called FROC, which is a localization score. How good are you at picking out these lesions? Our model got a FROC of 0.89. Now, for comparison, there was a pathologist with unlimited time who also tried to do this task, and the FROC was about 0.73. Again, we published this work online and made it accessible to other researchers. So now we're working with doctors to see how this actually can be truly implemented in a useful way. It's one thing to show this in a controlled environment. It's another when human beings are involved. And the second thing that we are working on is expanding this research to other types of cancers. So I've outlined a couple of efforts that's going on within Google in healthcare, but because TensorFlow is open source, it's available to researchers everywhere, and we're really excited about what other people have done with this technology. So you've heard the story about Abu. Another story that's actually quite inspiring is also a group of researchers at Stanford University used the same technology to detect skin cancers, and their model had accuracy that was on par with dermatologists. So beyond machine learning for healthcare, there are also many more examples of how this technology can advance scientific discovery as a whole. There are a number of startups and researchers that are using machine learning to speed up the discovery of new drugs and new therapies. There are a lot of researchers that are using TensorFlow to help make sense of genetic information, which is actually quite complex. So to summarize, there's a growing number of scientists working with computer scientists to solve tough challenges like healthcare, environmental protection, energy, transportation, infrastructure, you name it. And while the number is growing, we are just at the very beginning of what's possible. And that's why it's really important to provide researchers with tools like TensorFlow and to publish our results. With that, we'd like to show you one more example of how ML, or machine learning, is helping to tackle a tough social problem. I'd like to welcome Victor Anton to the stage. Victor is an ecologist at the University of Victoria in New Zealand, and he's using TensorFlow to help track endangered birds.
Hello everyone, my name is Victor Anton and I'm a PhD student at Victoria University of Wellington in New Zealand. My research aims to save threatened species in urban areas, so in cities and in towns around New Zealand. And today I'm going to be talking about how I'm using TensorFlow to identify bird songs. But before that, let me give you a little bit of information of why New Zealand birds are so special. I am originally from Spain, and I've always been interested in nature, especially in birds. And I moved to New Zealand because New Zealand is also known as the land of birds. And this is because of the high number of species that you can only find on this country. So, for example, 28% of the bird species that you come across in New Zealand can only be found on this country. 28% might seem like a low number, but when we compare it with other places, like here in Japan or Great Britain, it can give us a little bit of an idea of how unique these birds are. New Zealanders have a strong connection with their birds. For example, Maori people use their feathers as a sign of hierarchy. And nowadays we can see the native birds in different logos and trademarks. Even the New Zealand Air Force have a flightless bird as their symbol. And they are very committed to the birds. But not everything are good news for the birds. And they are currently threatened by deforestation, so they have less and less forest, and the habitat where they used to live has been modified. And they are also especially threatened by predation by introduced species. But as I mentioned, New Zealanders are very committed to their birds, and it's quite impressive to see the amount of people that meet up on a regular basis to plant native trees or to provide artificial nest boxes, or even providing artificial feeding stations for the birds in their houses. But today I'm going to be talking about another conservation action, the so-called fence reserves. Fence reserves are areas that are set aside for conservation purposes, and they are surrounded by a fence, a predator-proof fence. The goal of this fence is to keep predators out of the reserve, so inside the reserve the birds can survive without further conservation management. These fence reserves are very useful in terms of conservation worldwide, but they are especially useful for Australia and New Zealand. And inside the reserves, people can enter and they can enjoy the birds and they can learn about it and enjoy these special threatened birds. But what happens outside? The fence is around 2 meters and it does a great job on preventing the predators from coming in. But do the birds fly over? Is there a spillover out of these reserves? So that's exactly what I'm trying to answer on my research. So what happens outside this reserve? To answer this question, I selected one of the 16 sanctuaries that New Zealand has, and this one in particular is very close to actually the university where I am studying and to the city center in Wellington, the capital of New Zealand. So you can see on green on the highlighted map how it's really close to the city center. So if these threatened species jump over the fence, there's a big chance that people that live really close to the city center and in the suburbia, they can enjoy these birds outside the sanctuary. So to answer this, whether the birds spill over from these reserves, I started to set up some audio recorders, some voice recorders, and I set them up inside and outside the reserve, so on the orange points. And if, for example, we find that there is the same vegetation inside the reserve and outside the reserve, we can start to answer questions of why these birds are only selecting the vegetation inside and not outside. So yeah, that's my question. And it looked like a nice idea. So after 1 year, I collected 15,000 hours of audio, and I decided to start listening to the bird calls and to recognize the species. And I calculated how long it will take me to go through all this data, and I estimated that it will be 2 years of non-stop listening. I didn't really like that idea, so I contacted the Wellington brand of NEC, an IT company, and together we started to think about using machine learning, and especially TensorFlow, to reduce the amount of time that we needed to spend to classify all this audio, all these bird calls. The way that we do it is simple. We have the 15,000 hours of audio. We transform the data, the audio, into spectrograms. So spectrograms are a visualization of the audio. And then we listen to the spectrograms and we classify the spectrograms saying whether there is a bird or not and what is the species that is making that call. We feed into TensorFlow and we train some models. And then we ask TensorFlow to classify some of the spectrograms that we haven't classified. We validate how accurate the TensorFlow models are, and then we can start tweaking the models. So this is based on the premise that each bird has a different call and it has a different spectrogram. So for example, here on the top, we have kakariki, and that's the spectrogram of this audio clip. So we can hear it. So it has a repetitive call, and we can see that it's here at the bottom. And that is different from other birds. For example, we have at the bottom the hebe, and we can hear to it now. So you can see how different birds have different calls and how you can see that on the spectrograms. So let me guide you through a couple of examples of how actually we do this. We have the audio, we transform it into spectrograms, we listen to it, and we say, for example, the first one, we listen to the first one, and yeah, it's kakariki, so we classify it and say there's a bird call. We listen to the second one, that's not a bird call. So that is just noise. And we can see that the spectrograms look quite different. So yeah, we do this for several times until we get a trained model. And then we ask TensorFlow to classify new data, new spectrograms. And we can see what the TensorFlow says, that there's a bird call on the first audio, so we can listen to it. And we say, yeah, that's a bird call. And then we see that it seems like there is a bird call on the second one because it has a similar spectrogram. So we listen to it. But actually, no, that's not a bird call. That's just a bus stopping, a bus braking, the sound of a bus braking. So at the moment, we are validating the results that we get from TensorFlow. We are tweaking the models to make it more accurate. We are also working on a citizen science platform, so we can invite the general public to help us classifying the bird calls, so we can get more training data and more validation data faster. Because the ultimate goal of our research is to have a framework where we can classify the bird calls on real time, so people can go with their mobiles and start to recognize what is the bird call that they are listening. And this is going to be very useful in terms of first getting the people to know their birds and educating about threatened birds in New Zealand, but also it's going to be good for conservation actions because we can know where these different birds are, and by knowing their location, we can see how we should improve our conservation efforts or what kind of actions we should do. We should maybe put more effort towards planting native trees, or we should put more efforts on putting more artificial feeding, and so on. Overall, I think that having TensorFlow or AI as an open source, it enables anyone to use this technology. And when it comes down to biologists, this is great because we usually have a lot of data, but in order for us to analyze all this data, we need to classify it. And using this technology, it can help us to spend our time on a more efficient way. Thanks a lot for that.
Okay, thanks a lot, Victor. And we're almost at the end of our morning event. What have you seen? So you've seen a bunch of examples where we're able to take machine learning and AI and put it into our products, make our products more useful and accessible and intelligent. You've also seen that because we've open sourced a lot of the tools and made them available through our cloud platform as well, we are enabling lots and lots of businesses and organizations, people like Victor, people like Abu, to really use machine learning to solve their problems. We probably are not, as a company, you're not going to go out and find sea cows, but it's really important that we make the tools available so that everyone can take the basic underlying technology and apply it to the problems that they care the most about. And then Lily and Victor gave you a glimpse of how these tools can be used to tackle really difficult problems in healthcare, environmental protection, and a variety of other things. So there are more examples, but there are a few challenges we need to overcome as we start to deploy more and more AI technologies in the world. So first, it's really important that we increase access to machine learning expertise. And then also that we make machine learning be a fair and responsible thing as we start to deploy it in lots of products and things that are making decisions in the world. Let's talk about each of these. So first, access to machine learning expertise. Obviously, this is a relatively new technology, and not even every computer scientist has a deep background in machine learning. And so one of the things we've been doing internally as a company is to really train more and more of our engineers how machine learning works, how to actually use it in products, how to train models, how what kinds of approaches will work best, and what kinds of problems are solvable today, what kinds are not quite, and so on. And we've gone from about less than 1,000 people at Google who were trained in machine learning to more than 18,000 people today through internal education courses. And we've actually been piloting the same course we use internally with external universities. So we had about 1,000 people, university and technical professionals, go through this course, and they really felt that they got a lot out of it as well. And so we're going to be putting this course online, essentially the same material that we use to teach our own internal engineers early next year, so that anyone in the world can essentially get training from machine learning teachers and instructors that we use at Google, and get videos from AI experts at Google, interactive visualizations, coding exercises, to really enable more and more people to be able to understand how to use this technology. on the research front, one of the things that our group has been focused on a lot is, our training programs will allow us to go from 1,000 to 18,000 engineers within Google, and we'll eventually get that even higher. But if you think about the machine learning problems that exist in the world, there's probably millions of organizations that should be using machine learning today, and there's probably 1,000 or 10,000 that really effectively are using machine learning in a real production environment today. And so one of the things we want to do is, what if we could automate the process of machine learning? What if you didn't need as much machine learning expertise to actually get a machine learning solution? And the way this works is we're going to have a machine learning model that generates machine learning models. And essentially, the way that works is we generate a machine learning model, or we generate 10 machine learning models, and then we train those on a problem we care about. And we see which ones work well and which ones don't work well. And then we can use that signal as feedback to the machine learning generating model, where it can say, well, these ones didn't work very well, so don't do as many like this, and this one worked really well, so do more kind of in that game. And then we repeat this. And so we might generate 15,000 or 20,000 models and train them on a problem we care about. And this is actually a lot like what a human machine learning expert does when they're trying to find a good model. That's the process that Victor was describing, where they take their data, they try this kind of model, this one works pretty well, we're going to tweak it a little bit, and we're going to go back and do a slightly different model based on our experience. This is essentially automating that. And it works really, really well. It's the really good news. So what I'm showing you here is for the ImageNet challenge, which is a common popular competition for labeling images. You have images and 1,000 different categories, and you have to take an image and assign the correct category to each image. And the graph is showing you the computational cost of different kinds of models that have been developed over the last 4 or 5 years. And the y-axis is accuracy. Higher is better. Obviously, you'd like lower computational costs. So the place you'd like to be here is the upper left corner. And the black dots here are a progression of lots of improvements by top machine learning research labs around the world. Some from Google, some from Microsoft Research, some from universities over the years that have varying trade-offs of computational cost and accuracy. And so every black dot there is the work of months or years of accumulated research to produce a new kind of model that has better results than the previous best. And what you can see is that the red dots there are the models generated by this automated machine learning approach. And we're actually getting better results, both kind of at the right-hand side, we're getting higher accuracy with less computational cost than the best models. And at the left-hand side, we're getting much higher accuracy with the same computational cost for very low computational cost models, the kinds of models you might want to run on the phone or something where you don't have a lot of power available. And so this is really, really encouraging, because all of a sudden, anyone with a machine learning problem, at least of a restricted class initially, but eventually more and more kinds of machine learning problems, can get a solution automatically. Okay. The other thing I want to talk about is sort of fair and responsible use of machine learning and AI. We really want to make the benefits of AI accessible to everyone. And sometimes when you train, for example, on data, the data you train on reflects the world as it is, not the world that we would like to have. And so it's really important that we sort of find algorithmic techniques to correct for bias in training data, for example. So we have 2 things I'd like to talk about today. One is a new initiative at Google that's across lots and lots of teams at Google called the People and AI Research Initiative. And second is some work we've been doing with the Gina Davis Institute in Hollywood about bias in media. So PAIR really brings together researchers across Google to study and design how we're going to build systems that use AI in collaboration with humans. So a lot of these systems, that when they're deployed, they're going to have some way of presenting predictions or information or things like that. And it's really important that we figure out good ways that humans and AI systems can cooperate and interact to sort of get the best outcomes for everyone. And we're focused on 3 different classes of people. So one is we want to make tools that enable AI and machine learning researchers more effective as they're working on problems in this space. Second is we want to focus on domain experts, people like doctors or scientists, or people like Victor, who is an expert in sort of bird song, but not necessarily a machine learning expert. How can we make tools that enable them to really sort of make progress on the problems they care about? And third is how can we make machine learning accessible to everyday users across a broad spectrum of areas. And the goal isn't just to publish research, we're actually releasing open source tools for people to use. So here's an example of a tool more targeted for machine learning experts or people who are domain experts. So one of the things you first want to do whenever you have a new machine learning problem is you want to sort of really understand what training data you have. As Victor says, a lot of this data has noise in it, and you want to kind of understand the properties that it has. This is an example of a visualization tool where we're using a visualization of some data where we asked millions of users around the world to draw different kinds of objects. And we asked them to draw things like mosquitoes and boats and chairs. And so this is a visualization of the chairs that people drew, grouped by the country where the user is. And you notice even in some fairly benign settings like this, you can have interesting biases in the data set. So for example, the people who were looking at this data learned that people in Korea tend to draw, when they're asked to draw a chair, they draw it slightly offset, compared with people in other countries like South Africa and Russia, where they tend to draw it more head-on. Now, this isn't a particularly harmful kind of bias in the data, but it is kind of an interesting bias that you can discover with the right kinds of visualization tools. And so we're publishing lots of papers about making ML inclusive. One of these is the equality of opportunity in supervised learning. This is an algorithmic technique to make models more fair, for example, and lots of other papers. So we're pretty excited about this thread of research. Let me talk to you about the work that we're doing with the Gina Davis Institute in Hollywood. So many other industries have different kinds of biases. And in the media industry, for example, one kind of bias that crops up is gender bias. And if you have humans sit down and analyze the screen time that female characters and male characters get in different kinds of media, you'll find that there's a definite bias towards male characters. And this is kind of a tedious task, but you can actually automate this task with machine learning. And one of the things that the Gina Davis Institute collaborated with Google on is automating this task. And what they found was that they did then apply this model to the top grossing movies in 2015 and 2014. And they showed a clear underrepresentation of female characters. I won't go into all the details, but one of the things that they then analyzed in this data is that movies with strong female leads actually had higher grossing margins. So they grossed almost 16% more revenue. And so they were then able to present this research to studio heads and say, hey, look, it looks like having strong female leads is actually a good thing, both from a bias perspective, but also from a revenue perspective. And so we're hoping this will encourage studios to create more shows with strong female leads. Okay, so those are some of the things we're doing to make AI more inclusive and using machine learning to help find biases. This is really important work. So this brings us back to Google's mission of making AI accessible. What we really want is to make the benefits of AI accessible to everyone. We're doing that through creating AI in our products, through open sourcing our tools, and also working with researchers around the world, both inside Google and outside, to tackle the really difficult challenges that we think machine learning and AI can really have a big impact on. Things like healthcare, environmental protection, things like that. So with that, thank you for the prepared portion of our program. We're now gonna, I think, bring out a bunch of chairs and have questions and answers. Thank you.
Great. We have chairs and some of our speakers coming back on stage. to go. Hopefully questions in the room. I also have some from the 3 other rooms that have been watching this morning avidly. But why don't we kick off in the room here? So has anyone got any questions for our presenters? Oh, and there are microphones running around somewhere. Here we go.
Hi, Yulin. I'm talking for ZTNet in Singapore. Jeff, we talked about the need for fair, responsible development, which was interesting. But do you feel that there's a current pushback from the public of tech companies collecting data over concerns of privacy? And with the recent revelation that Google has been collecting location data, even though it's been turned off by the users, do you think that such news making headlines may kind of impede on the development of AI, especially when data is a huge component to feed models and to make it more intelligent? How do you balance that requirement?
Yeah, I mean, I think we've always had a strong tradition of giving users control over their data and allowing them to sort of understand what data that Google has about their usage of our products and how we use that to improve our products. I do think that in a lot of cases, many of the problems that we're tackling don't require human, user-specific data, and actually don't require very large amounts of data. A lot of the improvements here are through algorithmic improvements and sort of computational improvements, not necessarily through massive data sets. And I think, obviously, we want to use user data to improve a lot of our products, but give users sort of control over that data.
Great. I think we have another question in the room here.
Hey, Thomas Low from Ping West in China. Hey, Jeff. Yeah, just a question about TensorFlow platform. So we just noticed that as a AI or machine learning development platform for TensorFlow, and it's obviously now suffering some kind of the challenges by other platforms like the MXNet or Cafe, KISS MXNet and Cafe. Now it's obviously getting closer with Amazon. And now in China, Baidu has its own paddle. So how do you think about this kind of the challenge, like some kind of the big organizations or companies are worrying about using Google's TensorFlow to develop more things, rather some kind of small developers are truly welcoming TensorFlow. How do you think about this kind of the challenges for TensorFlow? And another question probably for Vinny Ha is about the translation. Just the language and linguistics is pretty highly culture relevant, and it's really dynamic. People just create different sort of the proverbs or the new phrases and new words, and from time to time through internet and through their daily life. So how this kind of the machine learning or this kind of the translation into the artificial intelligence into translation can catch this kind of the paces of the people's creation of their own language and linguistic to create better and more relevant and more high quality translation. Just sort of like that. Thank you.
Should I tackle the first one? So the first one, I think, there's definitely lots of open source platforms for machine learning out there, and I actually think that's great because they all are slightly different and have different strengths and weaknesses, and I think we can all learn from each other. So TensorFlow is sort of continuously evolving and adding new features that our users really request and that target different kinds of audiences like researchers or people trying to deploy things on mobile platforms or things like that. So I actually think that's a good thing. The TensorFlow open source software actually is released under a really flexible license. It's got an Apache 2.0 license, and that pretty much means anyone can take it and do whatever they want with it. And that actually has been a really good thing. I think that is part of the reason for the success of TensorFlow. People can feel like they can adopt it and actually use it in whatever company they're in a startup or in a large company. We've got lots of great contributions from other big companies. So Microsoft did some really nice contributions to TensorFlow to get it to work well on Windows, things like that. So we see a pretty healthy ecosystem, and we're learning a lot from other open source platforms and continually improving TensorFlow. I think that's how we continue to make it better.
I can't speak for Translate specifically because I don't work on Translate, but I can talk about it in language in general, right? So I think you touched upon something that's really important and interesting, especially along the lines of what I was talking about with voice, right? We know, for instance, Chinese, we talk about it, especially in the West, we talk about Chinese as if it's one language, but we know that this is not the case. Not only because there's a simplified Chinese in mainland China, the traditional Chinese in Taiwan and Hong Kong, but then you also have the spoken variety, right? Mandarin and Cantonese, right? So, and that's just the difference between the spoken language and the written form. And then on top of that, you have, when we were working on actually Cantonese, I was talking about this earlier, Cantonese was actually one of our first bilingual models because we learned right away by looking at the queries and looking at how people actually spoke, that there's a lot of English within their daily language and within their vernacular, and we wanted to make sure that we included as much of the English and Cantonese with, and then the written form of Jiping, right, and Pinyin in Chinese, right, mainland China. So to be able to pair the written variety and the spoken variety and actually create machine learned models is the tricky part. But one of the things I do know that we have been able to make huge successes with the neural nets model in Google Translate is the volume of data, and to be able to have little sets of really good data that really has improved the models for the Asian languages.
I'll just touch on one more item in your question, which is, I think another part of your question was, when you deploy a machine learning system, how quickly does the data you want to use in the system change? And different kinds of problems have very different paces at which that happens, right? Things related to user queries, for example, change day to day because all of a sudden there's a new chocolate festival in Tokyo and people are querying about it. Things like, very low-level speech recognition models don't necessarily change that fast because the sounds people make, don't really change day to day at the low level. And things like maps kind of change at the scale of humans opening up new businesses. So it varies a lot by the problem, but it is really important that the way you train your model, the distribution of data needs to reflect the data that you're actually testing it on.
Okay, just going to take one from Taipei, and my phone just locked. So Google has rolled out Pixel Visual Core on imaging. Will you roll out chips on voice input next?
I would say oh, sorry, maybe this is for the Pixel phone, or is this about TPUs, or?
I think it's yes, exactly, it's a visual TPU.
So we designed the TPU chip to actually be able to run lots and lots of different kinds of machine learning models. So the chips are not custom to a particular model. They're custom to run the kinds of operations that occur in lots of different kinds of neural nets very quickly. And so, for example, most of the work that you see here are models that run extremely well on TPUs. Things like vision models, speech models, language translation models, various prediction models. All of those take advantage of the core processing capability in those models, which is essentially doing really fast, low precision, high throughput linear algebra.
Great, perfect, thank you. I think there was a question over here.
Peter Marks, ABC. You've talked a lot about narrow AI, winning at Go, finding tumors, all great stuff. But the criticism or the warnings that have come from business, from Elon Musk and Bill Gates, they're all about general AI, broad AI, a machine that's really intelligent. Is there any work going on there? Is Google Assistant going to become conscious one day?
Do you want to take the conscious Google Assistant?
So our goal with the assistant is to make it useful for users. And when we look at doing that, we start with at least running user studies to figure out what are daily information needs that people have. And the assistant should be helpful, and that should be the primary experience. It's not about mimicking humans or solving this in a general broad sense, but things that we need help with, the assistant should be helpful in providing help in those instances and making your life easier and better so that you can do those tasks easier.
So what do you think of these warnings, these criticisms? Are you doing anything about it? Are you worried about it yourself? Are you putting in safeguards?
So, I think they're kind of very distant, very far off kinds of fears, and I don't think they're necessarily very realistic. I do think that as we start to deploy more machine learned and AI systems in the real world, where they're actually taking actions that can have serious consequences, there are very concrete and real safety problems in deploying these. Essentially, we now have systems that are learned rather than hand-coded. And that is a very different kind of system. You know, the way we make sure that coded systems are safe is we have a lot of good software engineering practices around testing and making sure that it works well in lots of different scenarios. And I think we can use a lot of those techniques, you know, altered somewhat for deploying safe AI learned systems. And so I think that's the more pressing kind of research to do in the short term. And these long, far off fears don't really seem actionable to me at the moment. Like, I think we're so far from, you know, systems that have those capabilities that it's not sort of the main point of concern right now. We should focus on the more pressing concerns.
Peter Griffin from RNZ, just in a similar sort of vein. Jeff, what, you know, as a leading researcher in this field, what is your ultimate vision for AI in your lifetime? I think there's a perception in the public that what you're all striving for is sort of true human level reasoning. Is it that? Or what is it for you? And what are the barriers you have to overcome technically to get there?
So, I mean, I think the question just before this about narrow AI is definitely where we are now. Essentially, the systems we're training are good at one or a handful of things. And ultimately, I think we want to make more flexible systems that can be sort of more useful. That would be good for the assistant so that it can, you know, answer any question you might throw at it rather than sort of a more limited domain of things. Ultimately, I want to build things that really help people achieve more than we could without these kinds of technologies. And I think we have great opportunities to do that in areas like healthcare, in sort of conserving the environment, in self-driving cars are clearly going to be, you know, a big impact on the world. They'll be good for the environment. They'll be good for sort of how we do urban planning, these kinds of things. And I think that's ultimately what we want to do, is make lives better.
Question here.
Okay, Jeff, I'm from Loyang, China. I have two questions for you. And first is, what's your opinions on Geoffrey Hinton's opinion about backpropagation and his work on capture? And the second is there any plan that Google will build a TensorFlow community in China, just like an Angel developed community? Thank you.
Sure. You know, I think, you know, Jeff's opinions about backpropagation change year to year. You know, he's obviously a brilliant scientist, and the capsules work I think is really interesting. It's sort of really, it's essentially looking for patterns of agreement at the lower levels with a sort of iterative algorithm before it progresses on to the next algorithm, rather than just sort of blindly propagating up information. He's been trying sort of a lot of variations of this approach for the last couple of years, and I think he's really hit on one that seems to be working well on small problems. And so I think the next steps for that are, you know, what does it actually do as we work on bigger problems? You know, I think the TensorFlow community in China is reasonably vibrant, and I think we want to do things to encourage it to be even more vibrant. So we don't have anything to announce, but that definitely seems like an area we want to work in. We're going to do things there. Okay.
Okay, great. Quick question from Korea. Lily, why did you focus on diabetic retinopathy and breast cancer? Any other disease research plans in the future? What's next?
Yes, so we started off with diabetic eye disease simply because that was, you know, the initial problem that our partners in India came to us with. We didn't have a research group in healthcare at that point, and so that was a pretty pressing need for them, and it was clear that we could help. It was a project that we started off based on that need. And as we were looking at places where you know, the variability in reading can actually have a high impact. That's where sort of the pathology project came along, and you can imagine that this technology works really well for all sorts of types of medical imaging. And so, you know, we're looking at other places where we think that this can really be good.
Great, cool. Thank you very much. I think there's a question up here.
Hi, Shruti from India. I wanted to ask about biases when it comes to training your AI models, and how easy or how difficult is it to weed those out, because something that you might not consider as a bias could be, it could, you know, work the other way in a different culture. For instance, recently I think Apple, it was reported that it was storing some photos in a bra folder. And I thought that was pretty strange that that somebody is training a computer model to actually recognize a bra, whereas there's no particular folder, say, for shorts or something like that. And in fact, I think even Google's photos can actually identify bras, which I thought is again odd. I get it that it needs to learn shirts, but the fact that it's identifying something, which as a woman I found that strange. So again, how do you keep out biases, and especially if you're moving on to automated machine learning models, which means the bias is already there, how are you going to weed that out if that's the future that you're getting?
Yeah, I mean, I think this is obviously a key problem as we start to have more of these models used for lots of different things. One of the key ways you can eliminate bias is to make sure that the data that you're training on is actually representative of the data that you're testing on when you're actually using it in a product. For example, you don't want to collect all your data only in the US and then use that model in India and Pakistan and other places. You want your data to be representative of the different sort of customs or local standards that exist. I think that's one way. The other way is you don't want to necessarily rob these models of all bias. Essentially, they are part of their power is detecting correlations and biases in the data that they see in order to actually make the useful predictions that they do. So when I see correlations of like whiskers and ears and things like that, and that tells me it's a cat, that's actually a good thing. If I train a language model to say that the word cancer and biopsy are related in some way, that's useful. But if I see that the word doctor is associated with he and nurse is associated with she, that's perhaps a bias that I don't want in the model. But that is the bias that it learns from real-world training data of text in the world. And so we're doing a lot of work on sort of algorithmic ways of removing biases that we don't want in the sort of machine learning models, but while retaining the biases of things like biopsy and cancer are related, because that's actually part of the power of these techniques. It's a tricky problem, and that's essentially a research problem and a problem that faces anyone trying to deploy a machine learning model.
Okay, I've got a question at the back here.
Hi there, Peter Wells from the Financial Times. First of all, thank you very much, all of you, for sharing your views and opinions today. Thanks, much appreciated. Question maybe for Jeff. A couple of months ago, Eric Schmidt had been talking about a race of sorts between China and the US in terms of artificial intelligence. And I think he suggested that perhaps it was only going to take 5 years before China might overtake the US in that respect. Just interested to see how you see that race playing out. And then, I guess further to that sort of main question, what sort of things the US could do if we were going to look at this from a US perspective? What sort of things the US would need to do or could do in order to maintain its lead or be in the lead? And then finally, what role do you see Google playing with that in terms of competition for hiring engineering talent? I think recently you guys opened up an engineering office in China. And I think that sort of comes with a suggestion amongst the media community or what have you that you could be drawing talent from Chinese operators equally. You are just a magnet really for that sort of thing. So I'm just interested on how you see that race playing out.
Obviously, I think there's lots and lots of entities interested in machine learning and AI around the world. There's many companies are interested in it. Many governments are sort of very aware of the potential for it to solve lots of problems in their societies and are at various stages in how proactive they are about investing and funding basic research and encouraging the ecosystem. I saw the report that the Chinese central government put out about AI, and that it seems like a pretty well formulated plan. The U.S. Government, I think, is not quite as organized in that respect, but also we tend to have a lot of our research happening in corporations and academia, which is a little bit more chaotic ecosystem than a more sort of central plan. But I think all of these things are useful, and it's clear that machine learning and AI have a lot of potential to affect not just computer science, but many industries. And so I think that's why you see governments and companies investing heavily. And part of that is trying to hire really good people who have these kinds of skills who are not that prevalent in the world at the moment. And that's obviously creating competition. There are lots of solutions to this. One is training more people with these kinds of skills. I think there's tons of interest in academic communities in entry-level machine learning courses. They're always oversubscribed by factors of 3 or whatever. So over time, I think more and more people will get these skills, and they'll apply these skills to more and more interesting problems.
What does Google need to do to maintain its edge in this whole?
Well, I think we want to focus on the next frontier of research problems and hire the best people to equip them with kind of the best kinds of computing hardware for these kinds of problems, and work on solving interesting and real problems, and not worry too much about what our competitors are doing, but focus on the research.
Okay, great. And it's worth reinforcing that we've had an engineering office in China.
Yeah. This is, I think there's a renewed emphasis on hiring machine learning people, but we've had an engineering office in both Shanghai and Beijing for a while.
Yeah, exactly. Question over here.
Hi, I'm Masahiro Nakagawa from Japanese business magazine Tomo Keizai. I have a question to Jeff. So about auto ML. So did that change the way you see in the future of machine learning over say like short term, 5 to 10 years? Like how do you think like accelerate the development of machine learning?
Right. I mean, I think this might relate a little bit to your question about how do we go from these narrow machine learning systems to ones that can sort of flexibly deal with more problems. And I think we obviously are starting to use this internally for a lot of our problems, where we actually have data sets where we can point AutoML at it and get better results than our ML researchers and engineers have been able to get on particular problems. So that's starting to have an impact within Google. We also want to bring this technology to external organizations as well, because we think there's a lot of people who have machine learning problems and have the expertise to kind of collect the right data and to maybe label the data for a supervised learning problem, but maybe don't have as much skill in how do you actually create a machine learning model. And we think these kinds of approaches can perhaps broaden the use of machine learning to much wider sets of developers and others around the world. So I think this won't be a 10-year thing. This might be a relatively short-term thing where it's starting to have impact in the world.
Okay, one more question from China. Isaac, probably for you. When did the development of pixel visual cores start? Beside HDR+, what else will be applied in the future, and how can developers make the most of it? There you go.
So we've been working on
Still not on.
Please switch on. We've been working on Pixel Visual Core for several years. It takes a lot of time to bring up an entire chipset, tool chain, get the drivers running, finally shipping the product, and the algorithm running on top of it. So HDR+, which is our low light and dynamic range algorithm that we use in virtually all the photos that you take with default camera pixel. Through Pixel Visual Core, we'll be able to bring HDR+ to third-party apps as well as default camera apps. So that's a huge advancement for image quality across all the apps that use camera on your Pixel phone. In terms of things we intend to run on top of Visual Core in the future, I don't really have anything to announce just yet, but like Jeff mentioned, it's a kind of core that's suitable for a lot of general kinds of workflows, things like imaging workflows, things like machine learning. So there will be more things over time, more and more things, but nothing specific right now. And I also don't work exactly on visual core teams, so I don't know what kind of tools and developer stories are looking at, but I'm sure we can get an answer.
Okay, great, cool. We're standing between journalists and lunch, so let's take 2 more questions. I've got 2 here. Yeah, please. And the lights going off earlier was the AI system saying don't ask long questions.
Okay, I'm Sriram from India. I'll keep it short. So we've heard about the good things that AI is doing for us, but it's also going to cause possibly problems such as job losses, like automation is already replacing jobs. So where does the responsibility lie, with governments or with companies like Google in addressing these issues? And specifically, and this is the larger question about bias, to handle issues such as bias and other problems. Do you have an ethics committee at Google to initiate policy discussions with government? What are you specifically doing to address the problems that technology will create?
Sure. I mean, I think that's one. Is that still on? Hello? Which?
The technical.
I'm going to try this one because this one worked before. Okay. So, I mean, I think the issues of machine learning and AI being able to automate some aspects of work is not a new thing. Like, this has happened with technology for the last 200 years. I do think here will be, what you'll see is that it may be able to automate things that we didn't consider automatable into 10 years ago. And so I think this is a general societal problem. Governments need to be thinking carefully about what their policies should be for people who are affected by this. But ultimately, I think every time technology has displaced what was previously human labor, I think we've gone on to create new and interesting professions as a result of on top of this technology, right? And I think that's clearly going to happen here as well. We'll have entirely new kinds of jobs that we don't even think of today. Who would have thought about social media consultants before the web existed, right? And so I don't actually know what those jobs will be, but there will be new kinds of things that once machine learning can automate some of the things that are more repetitive and simplistic, will actually enable people to accomplish more and to do more in conjunction with technology than individually. And for bias, I think we do have a responsibility here because we're sort of deploying machine learning systems and seeing that these AI systems do have bias, and we're actually doing fundamental research on this. I hope every machine learning organization in the world is looking at these kinds of issues.
Great.
That one seems less like a governmental issue and more like a AI research issue.
Okay, great. One last question.
Hi, Aloysius from CNET. So I guess AI in general is a lot more accurate than a human based on discourse. Are we ever approaching perfection? And I mean, in the case of in medicine as well, when you diagnose biopsies and even the blindness thing, how do you ensure that your accuracy is there? And what happens when it's misdiagnosed and it actually affects the patient in that sense? And then one more question is the moral problem of the trolley problem, where you hit 5 people or you save 1 person. What happens when what do you teach the AI there?
So I think in the context of medicine, I'll take that question in the context of medicine. I think, we've noticed that the machine learning models that we built are really good at predicting whatever label you give it, right? So if you give it what a human being said for a skin, based on a skin lesion, it will, model it'll give out what your doctor at some point said. Now, we also know in medicine, whenever we look at these kind of things, there's a better ground truth than just human interpretation. There's biopsies, right? And there's additional tests that we do. And then also there's a longitudinal aspect of how the patient turns out in the future. And so those are better sources of ground truth. And if you can get that type of label, you're going to get a better read on how the patient will actually do, and that's exactly what we do when we're reading these images. We're actually projecting what we think will happen to the patient. And so again, I think this is a point where we can actually use AI to even do better than what we have right now, to push the limits of medicine and really contribute to clinical research in that way. So that's actually really great. I don't know if we'll get to perfection because there's always this, some uncertainty about how the patient will turn out. So even if you got really great data about what happened to the patient, I think there will still be some uncertainty that you can't account for in these systems.
The trolley problem. I think that's a bit of a false problem. It's not like anyone is in there writing code saying, if I go right 3 people, if I go left 2 people, right? It's much more like a human driver, right? You're trying your best to, not have any accidents. And I actually think, autonomous cars, which I think is the context you're asking this question in, have a tremendous number of advantages relative to human drivers. They don't get distracted, they're not going to be texting, they can see in all directions at all times. So I think, there undoubtedly will be problems as these technologies are deployed, but I think they will actually end up being much safer than human drivers, and they don't have code in there that is making these sort of explicit decisions. They're essentially trying to be safe at all times, and I think they will actually end up being safer.
Fantastic. All right. Thank you all for your questions, and I want to thank our speakers who've joined us here today. The lunch is through the room that way, so if you go through that door, and there is a photo wall, there's going to be a quick opportunity to get some photos of some of the speakers as well, as you file your stories.
Thank you.
So we're going to head through this way. Thank you very much. Oh, no. Only the speakers that way, everyone else this way. There we go.
Okay.
I got it wrong. Okay. Well, you'll meet on the other side. Thank you very much.
저희 오늘 너무 장시간 3시간 동안 고생 많으셨고, 저희 오늘 크게 3가지 AI를 저희 제품이 어떻게 유용하게 활용하는지, 그다음에 구글 밖에 있는 개발자나 기업들이 어떻게 혁신을 할 수 있도록 도와주는지